And he will tell us a love story, so give him a big hand.
Hi, good morning. Thank you for being there. Okay, this is a story about love. So I think that it's the moment to talk about love. What is the meaning of loving what you do? It's not a rhetorical question. I want an answer from you. I really want an answer. What is the meaning for you of doing what you love? Go on.
To commit with all your heart to something and to grow in knowledge, and that way you get passion and you love what you do.
Perfect. Passion, it's a keyword.
Love one day, hate Friday.
Yeah, that's one. Other?
Never get bored.
No one else? Okay. All of those were good answers. Okay. I have another question for you. And what do you love? It's another non-rhetorical question. What do you love?
Myself.
Coffee. Me too. Those are good answers too. I can say to you what I love. I love coffee, obviously, but I love innovation, okay? And thankfully, I'm not the only one. I'm lucky enough to work with people that love innovation too and bring innovation to the world every day. I don't work in Wonderland, but I work for Second Quadrant. I'm Giulio Calacoci, I'm an open source developer, and every day I work with Python, writing in Python for Postgres and with Postgres. If you want to tweet something, you can use the EuroPython hashtag or the PMPLove hashtag for this talk. So, I promised you a love story, probably one of the biggest love story of all. There is the match made in heaven between Python and Postgres. You can see the elephant and the Python in love between each other, because one of the questions that I've been asked, not only yesterday, but also in different conferences, was, but Python and Postgres get along together well? And yes, a lot. They have a lot of things in common. Really, a lot of things in common. First one, the first letter is a P. And they are both open source. Both of them have a huge, really huge community that is really involved in the development of the programming language and of the database. In the case of Postgres, the community is responsible for the robustness of the database. Both are powerful. Python is powerful, is flexible. Postgres is powerful and stable. And both of them are really well documented. You can find a lot of documentation on a lot of stuff on the internet on Python and Postgres together. You know already Python because this is a Python conference. So please, allow me to introduce you Postgres. One important thing, the name is PostgreSQL, or Postgres, or if you feel like a close friend, PG, okay? If you call Postgres like this, the elephant will be happy. Please don't call him Postgre, or PostgreSQL, or any other iteration between the letters of the name. Otherwise, the elephant will be confused. I'm not sure that he will answer your questions. Okay. Postgres, or PostgreSQL, okay, is de facto the default database choice for many Python developers. There are a lot of developers around the world that have chosen Postgres as a default database for the application. Obviously, Most projects support more than one database, but usually tests and development is done on Postgres. Why? Because Postgres is free as a speech. Postgres is stable. Postgres is feature-rich, and we are going to see just the tip of the iceberg of the features that are part of Postgres. And Postgres is released frequently. Postgres is released once a year with a big release with new features, and one time every 3 months with bug fixes and minor features. We have a lot of features because it's feature-rich. In Postgres, the first one is the MDCC, that obviously is not something that only Postgres implement, but it's something that Postgres support, and is the multi-version concurrency control. That is something that makes you sure that your transactions are isolated between others. So when you do something, your database is always consistent. Because the first directive for a database is to keep your data safe. And Postgres, it's particularly good in doing that. I've seen databases during my work crashing in really bad ways, but I've seen people recovering the data until the moment of the crash. So Postgres is safe. Postgres have the transactional DDL. That is something that is less common than MVCC. And basically, when you do a change to your table, for example, you drop a column, okay? If you do that on a transaction, that action is transactional. Every operation that involves changing your database is safe and transactional. So who is working on the database on that moment is safe until the transaction is committed. It is something that not happens in every kind of database. Every biggest database that, like Oracle, does not support something like this. Okay? Postgres support tables inheritance. Tables inheritance is something that allows you to create a father table with a lot of one or more child tables that allow you to split your data in subtables and access them through the father table following a logic. And from Postgres 9.5, you can do that also on remote servers. So you can split and shard your data on remote servers and split evenly the data and the load on different instances of Postgres. Postgres support full text search. Yeah, something is really important, especially for people that use Django and develop in Django. It's so important that Django have a plugin that allows you to use full text search on Postgres easily. Then we have the replication. Replication is something that allows you to create a new a server that is a master and clone the server on another instance that is a standby. The standby is always synchronized with the master, and in case of disaster, if the master goes down, you can promote the standby and reduce to the minimum the downtime in case of a bad situation. Then Postgres supports physical backup, and this is cool because, at least for me, because I am disaster recovery expert, okay? Physical backup is something that makes you copy your data directory while your service is running. You don't have to stop your server to make a backup. And you're going to copy the physical file of the server and not asking for a SQL dump. So everything happens while the server is running with no downtime for you. So taking backups, it's easier and it's faster, okay? Postgres supports the point-in-time recovery. That's it, like a kind of magic, because if someone drops a table at 10 o'clock in the morning, you can recover your database at 9:59 and restart just a second before the disaster. Then supports JSON-B. JSON-B is a specific type of data that was thinking for people that like to use JSON, especially people that may like the NoSQL type of data that can store entire documents written in JSON inside your database, so you can mix between a relational database and something different. And another cool thing, and we will talk about it later, okay, but now I introduce it to you, are the foreign data wrapper, FDV. It allows you to connect to every kind of source of data outside the database. For example, you can connect to another database, not only Postgres, but also MySQL, Oracle, DB2, or you can use as source a text file, you can use as source a remote service. You can use everything and import in your database as a table. And you can do queries on that, and if the remote source allows it, you can also insert data, okay? Right straight inside your database. Okay, and we have also PostJS. PostJS is geospatial extension that adds extra types, extra functions, extra operations, index enhancement for handling geospatial data. They have, PostJS have a lot of functions that allow you to move inside a geographic area and find points that are near. And it's very important for people that develop using GIS. The relation between Postgres and Python is a virtuous cycle because, as I said, a lot of developers, Python developers, choose Postgres. And because of this, the software that is based on Postgres and as example that are based on Postgres and documentation that are for Postgres, it's better than the other. So more people is going to use them. So PostgreSQL community grows. If the PostgreSQL community grows, the database goes stronger. If the database goes stronger, more people is going to use Python and Postgres together. And this is a cycle. Because of this, the Python community grows and the cycle restarts. And this is important. But now it's time to talk about the love story, and let's get down in business. This is a showcase of things that have been done using Python and Postgres. And because a lot of people asked me, okay, but can you tell me at least a couple of projects that have been created using Python and Postgres? Sorry. Yes, I can. I created a talk on that. So, fifth thing. We want to connect to Postgres using Python. We have a lot of Python ORMs, like SQL Alchemy, PV, Pony ORM, and Django ORM, okay? They are written in Python, and they handle Postgres. And they have one thing in common. Every ORM that I named uses PsychoPG2. It is, no, clap your hands, because it's a moment of Italian pride for me, because the main developers of PsychoPG2 are Italian. Oh, really? So PsychoPG2 implements the Python DB API 2.0. It's based on libpq, that are the libraries, that are the standard libraries for Postgres. And it's open source, because LGGPL. So, it's really free. It's really easy to use. So much easy that a lot of people use it, and I've seen projects around the internet wrapping PsychoPG2 to create an even easier interface for that. So it's really, really powerful. Obviously, it's not the only one. There are a lot of other drivers. These are the most famous. We have PyPostgreSQL, PyGraphQL, PG8000, OCPGDB, and a lot of words and letters together. But By the way, PsychoPG2 is not the only one. There are a lot, and everyone is valid. Okay, what if I tell you that you can use Python inside Postgres? Every, let's say, serious database usually have an internal procedural language that allow you to write procedure to handle your data in a faster way that you would do in an external program, okay? Postgres allow you to load Python inside the database and use Python and these libraries inside your database to modify your data. You can use Python to react to action like insert or update, or you can use it to prepare your data for a huge dump of data, or what you want. You can use Postgres in Python, Python inside the Postgres, and write Python code inside Postgres. And this adds the flexibility of Python straight inside Postgres. But wait, I promised you that I would talk more about foreign data wrapper. As I said, you can use the foreign data wrapper technology to connect to something external. Usually, as I said, foreign data wrappers are written in C. But if you use Multicorn, that is a software that is written in Python, you can use Python to write foreign data wrappers. In the 2016, in the Italian Python conference, I've had a talk on this, and I written just for fun 3 foreign data wrappers, where I think the longest one was 150 lines of code, comments included, that allow me to connect, for example, to SoundCloud and query the service asking for songs straight inside the database, and then I was able to see the results of my research on a table. And that project started because I was really trying to organize my music collection, and then Postgres helped me to do that. If you want to see that, you can find the code on my GitHub, is that one. There is also a video, unfortunately it's in Italian, so if you don't understand Italian, you can skip that. Another thing that you want after having loaded the data through foreign data wrappers, having loaded Python inside your Postgres, is to back up your database, because I really can't stress enough people of the importance of making a backup. You can do that using Python. There are a couple of software that allow you to do that. The most famous are Wall-E, that is a really nice program that really acts nicely with AWS and S3 from Amazon. And another one that is a bit famous is Barman. So let's talk about Barman. Why you would like to use Barman? Because it's open source. It's one of the most used backup tools for PostgreSQL. It's feature-rich. It's easy to use, because one of the points that the developers have while developing it is to keep it simple. And it's developed by a team of nice people. How I know that? Because I'm one of those people. I'm one of the Barman developers. So let me introduce Barman for a bit. We are going to release the 2.2 version. The alpha version of the 2.2 will be released on July 17. And the killer feature that we are going to introduce is the rsync-based parallel backup that allow you to copy faster, and really, really faster, because we have done some tests on that, copy a huge database on your backup server. And this is important because, like I said, more people use a Python software with Postgres, the better the software become. And Barman is an example of that. I can say that because I worked on Barman for a lot of years. And Barman growth stronger because of the people that reported back to us that founded some features like this one. And now, if Barman is stable, it's because of this. Okay. I'm not able to pronounce correctly. Okay. So I'm going to call it HA, okay? The meaning of that word is that you want your database to be available to all the people most of the time, because if your database is down, probably the one of your concurrent is not. So the more you reduce your time, the better it is for you. How you can handle that? As I said before, we have streaming replication that allow you to synchronize more than one server with your master. Said so, how can you handle the promotion of one or more servers in case of disaster? You can use this Python software that's called Patroni, that is written by Zalando, so it's used by them. It's open source because I have an MIT license. It's written in Python, and it's based on Zookeeper or etcd or Consul, because you have more than one option. It depends on what you know. It's really powerful, and to explain it simply, when your database shuts down, your master, there is a discussion between the other nodes that decide which node will be promoted to the master, and it happens almost automatically. Okay, so no more calls at the middle of the night because the database is shut down. Obviously, we have to recover it, but you can do it the morning after. We have talked about database, we have talked about HA, now we want to handle our database, maybe easily. There are a lot of tools that allow you to do that. We have the OmniDB tool that's open source and have been recently rewritten using Django. Okay, the 2.0 version of this software has been rewritten from scratch using Django. It's cross-platform and have a nice PostgreSQL editor. And this software is written by two really amazing guys from Brazil, and now they work for Second Quadrant, are my colleagues. Then we have another tool that is historically, works historically near Postgres, okay, is pgadmin4, that is open source, it's multi-platform, gives you the ability to see the plan of your query, because when you create a query, Postgres analyzes it and decided how to act. You can see the plan that Postgres created for a query, and you can see if you can optimize your query to be faster or to act differently. And another thing, and it's really, really, really useful, especially for developer, gives you the ability to debug the procedural language that it's called PL/PGSQL while writing storage procedure. So usually it's not easy to debug storage procedures. You can do that putting a breakpoint on your code and step by step analyze it. After the graphical interface I showed you, because OmniDB and pgadmin4 are graphical, okay, we have the command line. That is the tool that most of the DBA or the sysadmin loves. We have the default client tool that is PSQL, that is part of the core of Postgres, is released with Postgres. It's really powerful, and it's born to work with Postgres by the people that develop Postgres. And have a lot of meta comments that allow you to perform actions like retrieving descriptions of tables, retrieving descriptions of schemas, or following foreign keys, or listing database just with a / command. Usually it has backslash and one letter, so it's faster and easy to use. But obviously it's not perfect. I have some issues, and browsing the web, searching for tools, nice tools for this presentation, I've discovered that exists PGCLE that is obviously less powerful than PSQL, but gives you syntax highlighting, smart completion, and always try to pretty print the output of the tables on your terminal. Obviously, it's not like PSQL, but if you have to write just a quick query, it's faster. Okay? And the smart completion is obviously contextual of what you're writing. The last one is the workload analyzer, because you want to monitor how Postgres behave. You can do that using this software that is developed by Dalibo, that is a French company that works on Postgres like Second Quadrant, that is open source and is composed by two parts. One part is an extension that resides in Postgres and is written obviously in C because it's part of Postgres. And one part is the user interface that is entirely written in Python and allow you to see real-time graphs and see performance chart, so you can inspect your database while it's working and see when or why, or it helps you understand why your database is under load on that moment. If you have a huge amount of logs, or this fault of a couple of queries that are really long, for example. You can do that only monitoring your database. And this is a Python tool to do that. What I show you is just the tip of the iceberg of the possibility of the things that are around the world written in Python and Postgres. What I show you is the result of love and passion, and that's why I said that passion is a keyword for this talk. What I want from you is to get involved and spread love and being part of the virtuous cycle that I showed you before. To do that, participating in conferences like this, or like these two, that are the next conferences on Postgres, okay? That is, we have the Italian PG Day that it's going to happen in Milan in 2017, 13th of October, or the PostgreSQL Conference Europe that will happen in Warsaw on October 24, 27, 2017. In this conference, in these events, you can talk with people that write the core of Postgres. You can talk with people that are there to help you to write better Python software with Postgres because it's their job. So it's important to meet these people and to get involved in that circle of virtuous cycle. Thank you.
Okay, thanks, Giulio. Who has questions for him? You.
Thank you for interesting presentation. I'm curious about. Oops. I'm curious. Oh, okay. I'm curious about PO, which you, as I understand, allows you to get some statistics how the Postgres database works.
Okay, sorry, but I can't hear you because the microphone is not working.
Okay. I'm curious about POVA, which is allows you to see how Postgres works from the presentation. If you try to use it, does it affect performance of the database during collection of the statistic, or not really?
Collecting? Okay, no.
You just don't hit.
Sorry for the technical issue. So, you heard the question, I have to repeat that? No, okay, he asked me if the workload analyzer could impact the performance of a database. Okay, yes, it could, marginally, but if you're in a situation that your database is always under heavy workload, okay, maybe you want to spend a bit of horsepower on trying to understand what's going on. It's something you can deactivate. It's an extension, it's part of Postgres, but you can turn it on and off. So you can turn it on when you need it and turn it off, not impacting your performances. Fine? Okay, good.
Okay,
other questions?
Kind of simple. So we have like a table of 100 million records, right? We want to do select one. So is there anything specific to Postgres that's going to allow us to do faster queries and searches than, let's say, MySQL or some other database? So if we have like 100 million rows, right, and you want to do a select query, just select one from those. Is there something specific to Postgres that's going to allow us to optimize the database, like clustering, indexing?
I'm repeating the question because, so I'm sure that everyone heard. He asked me if exists something that helps you to create faster queries. This is the sense of your question, right? Helps you writing faster queries. Yes. As I said, pgadmin 4, for example, makes you see the plan of a query. So you write a simple query, that just like a select star from something with 1 million rows, that for Postgres are not a lot of rows, to be honest. And you can see how Postgres intend to act on that query. And this is graphical. You see what happens, and you can decide that you can work and split easily that query in a query and a subquery, or something that's more performance-like. It depends on how Postgres reacts. What you are searching is just inside the database. It's part of Postgres.
Okay, another question? Someone else?
By the way, I will be at the second quadrant group booth in the Piazza room. Okay, so if you have questions, you can find me, or you can search for this guy. Stand up, Marco. Okay, for the technical question, or if you want to ask something that is more marketing or stuff related, you can ask to that girl that is there, or to the girl that is into the booth. Okay.
Okay.
No question down there.
Ah, I didn't see you.
Thanks a lot for your talk. I'll try this. Can you hear me? Okay. You talked a lot about the relationship between Python and Postgres, and I actually know this pretty well because we work with both at my company. But I'm wondering, for other people who don't have experience with PostgreSQL yet but are already Python developers, do you have any good how-to material or introduction, so how they can learn more about using PostgreSQL with Python? Because I think people are pretty familiar with databases in Python, so they might be using Mongo or MySQL or something. How can they get started with Postgres? Do you have any tips for them?
I like to work. Okay. So he asked me some tips, okay, to getting started in Postgres. Maybe migrating from MySQL or Oracle stuff, right? Okay, probably the biggest tip I can give you is read the documentation. Because Postgres documentation is really, really organized. And you can find what you need, exactly what you need, just with a simple search on the documentation website. There are a lot of tutorials on how to install Postgres, and usually for biggest distribution is just a command line line and getting started. It's almost pure SQL. Postgres is almost pure SQL, not strange construct. So if you know, generally speaking, SQL theory, you're able to use Postgres just out of the box.
So one issue you have when you're developing for a database is that you wind up with a bunch of tables. Oh, can you hear me? Okay. So one issue that we have when we're developing for databases is that we wind up with the schema. We may have hundreds of tables. We may have, dozens of store procedures, functions, everything like that in the database. What is the best way to organize and to manage that process? And do you know of any tools that allow you to actually manage and keep all that stuff in sync? You can do it on the command line. Yes, you can do it on the command line. But are there tools that allow you, for example, that if you have a store procedure and you make a change to that store procedure, that you can automatically publish all the changes to the database, from your repository?
Can I answer using that? Yes, okay. There are tools, you have heard the question? Yeah, okay. There are tools that allow you to do that, are not written in Python, so were not part of my presentation. There are tools that allow you to keep track of your changes and diff different schemas, see the changes, patch the schemas, and reload them. Then there are techniques of using Postgres that allow you to do that with less impact. But our techniques are not a specific tool to do that. But in my experience working in second quadrant in these years, I've seen people doing a lot of strange stuff to do that. And I've always seen that working. So Postgres is tough. It can handle every kind of change, and because I said it's transactional. You can try that. No, it's not. Roll back. Everything is good. Okay? Perfect.
So another question?
It's more a follow-up remark. It's more a follow-up remark to what you just asked. There is Alembic from the same author as SQL Alchemy that is a Python tool to track schemas. He knows more, I guess, but doesn't do everything, I guess, but might be worth looking into.
All right, one more?
I would like to finish
Okay.
and say one thing. If you search on Google for Postgres is awesome on GitHub, okay, you will find a web page that have a list that is always updated of software for Postgres. So we will find the tools you were asking, you will find the collection of tools for Postgres. And if you don't know that, there is also Python is awesome. Okay? Thank you.
All right.
Thank you very much. We had a little bit of trouble to get this slide. It worked perfectly on my screen, but connected with the projector, changed resolution and all of this off. So it's supposed to be programming in parallel with threads, a scientific use case. So I would like to give you a use case of what you can do with threads. I'm pretty focused on the use case, and then show you one solution what you can do with threads and where they're pretty useful. So the use case is a scientific application. So we'll go into a little bit how this scientific application is what's supposed to do. And we're talking about contaminations in micro concentrations from agriculture and domestic housing. So you apply a lot of chemicals when you do agriculture, and then you have a house, you have a paint, and then the rain washes off some of the paint. So we talk about very, very small concentrations here, and we have a use case. We have the River Rhine, which is a very big river in Europe here. I will show you in a minute, and that's this area. So it's a bit out of the screen, sorry, but that's the best I could get in time here. So microcontaminations, so very small concentrations. So if you now know to micrograms per liter, the liter is not there in the river. They have biochemical effects on water organisms. They can be pretty strong. So for instance, herbicides inhibit photosynthesis. And this has a very big impact on the whole ecosystem, because if the photosynthesis is where everything starts, where all these organic substances are produced, and this is inhibited, then there might go something wrong in the ecosystem. Likewise, chemicals can inhibit reproduction of fish. And currently there are more than 100,000 registered chemicals in Europe, so it's a lot of them. And this simulation model is just we will see how it works. Should be able to model most of them. Okay, some of the sources. So we have diffuse herbicide combinations from agriculture. You see here we have agriculture at different places, and you can see here you apply lots of chemicals like herbicides, and they are moved. Not everything is actually used for the purpose. Depending on the precipitation and the rain, some of them is washed into the river. And this is diffuse because it's widespread over a larger area. So that's one source, agriculture herbicides. The second source would be diffuse and point source combinations from buildings. So if you have buildings, then you have chemicals that are used for constructing the building, painting, for instance, plastering, and then when it rains, the rain carries very, very small amounts of this stuff, and it finally ends up in the river. You have also contamination from households, like contaminations, medication, radio-opaque substances. So if you go to the hospital and you eat it to get a better picture for X-ray and something like this, then eventually it will end up in the river when you go back home. Cosmetics, household chemicals, artificial sweeteners is very interesting. Per definition, they don't have any calories, so it's not attractive at all for any microorganism to break them down. But they don't break down, they can accumulate in the environment. And also effluent from sewage treatment plants. They are pretty good nowadays, but they don't get everything, especially those small concentrations of all kind of stuff, they won't be able to get it out. Okay, at the catchment area of the River Rhine, you see here it's more than 1,200 kilometers long, and more than 800 kilometers of them you can use a ship, you can navigate on there. And the area is about 185,000 square kilometers, and the discharge varies between 1,000 and 2,000 cubic meters per second, depends where you are, and there are about 58 million people living in this area. So this would be the area. That's called the catchment. This green thing is called the catchment. That is the area from where the water actually finally ends up in the river. So all excess water from precipitation will end up in this river. Okay, and this is just the big catchment, but it consists of about 18,000 sub-catchments. So small areas, you can see here, you see the river and all these tributaries, so small other rivers that flow into the River Rhine eventually, and it's 18,000 of them, and you can delineate them in space. It's depending on the surface. Yeah? So always the water flows down, and then you always say, okay, this flows this direction, you have different areas. Sub-catchments, we call them here. Now, let's have a short look how these numbers come about. So we have a lot of statistics. So you know about how much medication the average person consumes per year, and how much of this will be actually ends up in the wastewater. And you know roughly how much of this will be removed in the sewage treatment plant. And also, some of them are used in veterinary science. You know about a lot of animals get a lot of these medications. And then, typically, this is just a function of the population density. That's a population density. Dark colors means a lot of people. White means very few people. And you can see where people live around Zurich, and here in the rural area, and this one, and big cities. We have a lot of people, and of course, more people have more input into the river. Contamination from agriculture is a bit different. So you know about how much herbicides are usually used per crop, and we know what crops are growing there. And there's a loss rate. So the loss rate depends on the precipitation. The more it rains, the more it's lost. And also it depends a bit how the rain goes. So if there's a very strong rain, it might be more than if you have a little bit of rain all the time. And you see it's different. It's not at the big cities, of course. It's more where the agriculture areas are. And you see this. That's wheat here. See where a lot of wheat is, you know how much they apply there. These are the statistical numbers that will be data into the model. So what are the available data? So we have local discharge as a time series. So we will see this. We have hourly data for 1 year. We have land use data. So we know if there's agriculture, if there are cities, and how many square kilometers or square meters of this will be in these catchment areas. And we know when these substances are applied over time. And also we know the loss rates and decay rates of these substances. Some of them decay, some of them don't. So little that we can neglect this decay, so the amount will be reduced. There's some prior art already, so this project didn't develop all the software. There's one external program written in C++, but we only use executable, and this calculates the concentration loads for one catchment. Yeah? So this is for one catchment and for one substance. So we have this for one catchment. And typically it reads an XML file with all this information. And then it also reads a CSV file with this time-varying data. I will show you in a minute. And spits out a CSV at the end. So the result will be a CSV file. So that's how it looks like. So we have this XML file. It's just a typical XML file with stuff inside, and you see it describes what the substance is and some of the features of the substance. Yeah, it's not very big. That's it already. So that's a few things, and many of them don't really apply. Yeah, so the general, and also you specify the name of the input file. This is the other file we'll show in a minute, and some of these features, what it is, and some of things what the model is supposed to do. Okay. Time series is also very simple, so we have this time step. So we start, in every time step stands for 1 hour, so about like 9,000 time steps, process for 1 year, and we have a temperature, degrees Celsius, precipitation, which is starts with 0 here, and we have a discharge, so we know how much actually water flows for every hour from this sub-catchment into the river. Okay, the result will be a file that looks like this. So again, we have this time step here, which is also cut off. This is supposed to be step. And it echoes back the input, and then it gives you, this is the most important number, this is the concentration. In this case, it's atrazine, which is one of the substances. So that's what comes out. Okay. We had to prepare the data a little bit because we have 18,000 catchments and we get them just in the wrong format. Though there is a file with 18,000 columns, but we need 18,000 rows, so we need to transpose these ones. I've done it with pandas. I don't talk about the details how to do this here. It would be a different topic. And the land use data also in a DBF file. We have the DBS file. We have to read it from there, as well as the sub-catchment connections, which will be used for the next step. Okay. So what do we need to do? So first we have to get the data from this big file, as I said, rearrange these sub-catchments. And that's actually what I want to talk about, this red box here. So we have to calculate the loads and concentration for each of these 18,000 sub-catchments. And finally, I have to rearrange the data again because I need them per time step, not per catchment. So that would be another post-processing step to rearrange the data. Okay. Now, this is what we want to do, so we want to calculate 18,000 catchments. For each catchment, we get some input data, and then we run our external model, and we get some output. Of course, I programmed everything in Python 3. I think I saw with Python 3.5 at the time, but everything is running with Python 3.6. We use NumPy, pandas, and PyTables. So because we store all the data in HDF5 format, which is a scientific format that can hold a very large amount of data, so you can have terabyte-sized files if you like. In this case, it's not that big. The output was just 6 gigabytes, so not that big. Okay. So we calculate the load and concentration for one catchment, and that's what we need to do. So we get those data from this HDF5 file, where I put it in. We generate the input files via this XML file. So I use a template, and I just have to fill in those missing things. This is not much. And also we have to generate this time series for the temperature, precipitation, and the discharge. Then we need an external process and wait till it's finished, and then we have to read the output from the external process and process it further. So there's 4 steps. And now we come to the core of this talk, actually, a case for threads. Is this a case for threads? So you might know CPython, so the standard Python has this what's called the global interpreter log. So even CPython supports threads from the very beginning. It uses operating system threads, and hence all the threads work as operating system thread. But actually they don't run in parallel in terms of CPU. So if you have CPU-bound tasks, then even if you have multiple threads, they all run one after the other, and they never run exactly at the same time. So if you have CPU-bound problems, threads don't make sense, because actually it will get slower, because you have overhead switching from one thread to the other. If you have I/O-bound, input-output bound tasks, like reading and writing a file, starting external processes, then threads make sense, because when you have input-output tasks, then Python releases the GIL, the global interpreter log, and you can take advantage of the threads. So this is very important. If you want to use threads, you typically have to work on the input-output bound things, otherwise you won't make things faster. Unless you want concurrency and you don't care about making things faster, that's also fine, but you only release the GIL when you have input-output. That's a very important fact. So now let's re-examine our steps we have here. And if we go to the steps, then we see all of them actually are pretty much dominated by input-output. We generate files, we write files, we start an external process, which is by far the most time we spend, we'll see, and then we wait for the result, and then we read the outputs. So most of these tasks are input-output dominated, input-output bound, though we have a use case for our threads. Okay, this is a big picture. What happens? So we have a main thread, and we have workers. These are the acting persons you want to speak. So here in our process, the main thread is interacting with the data. It reads the data from this big HDF file, and saves the results back. And then it distributes the work to each worker. So it starts a new worker for each calculation. Yeah? The worker does their task. We will see this in a minute. So the worker actually is doing the calculation. And then the worker doesn't return in this case, but the worker puts the result into a queue. So whenever you can, when you work with threads, you should use queues. Don't try to do locking. So there's another thing. If you want to work with different threads, you can do locking, but it's really not recommended, because it's very, very difficult potentially to debug these things. Here I use a queue. So each worker is doing something, and when it's done, puts the result in a queue, and the main thread taking the result from the queue. So that's maybe come back to this picture. So actually, I do start a new thread for each worker. And now is the question: isn't it inefficient? Wouldn't it be better to use a thread pool? And maybe it's maybe more elegant to use a thread pool, but in terms of efficiency, I did a short test, and starting 18,000 threads and joining them back takes about a second. Yeah, more or less on my machine. But the total runtime of my whole program is 2.5 hours. So 1 second versus 2.5 hours, it doesn't really matter for this use case. For this use case, it doesn't matter if you start so many threads and kill them after this, because you can potentially gain maybe half a second or up to a second if you do this. And if it's 2.5 hours runtime, you can forget it. Yeah. So always, sometimes it makes sense to use thread pools. And here, this case, in terms of time, it doesn't give you any advantage to do something like this. Okay, so let's have a look at the code here. So how the code works. Oh, it's still so moved. I don't know why it's so shifted here. So this is the source code of the thread. So I import threading and the class thread from the threading module from the Python standard library, and I need to inherit from thread to make it a thread. This is a worker that's doing all the work. And you see, this has a lot of methods, but all of them have underscores that mean they're only used internally inside the thread. So the thread has to generate the input files, which is either first the XML file and then the time-varying file that's doing some work, has to execute the external program, run it, get the result, then read the output of this. So these are the tasks the worker has to do, but the only thing that's really concerned with the thread is run. So I have to override a method called run, and then we will see when you start the thread, this method will be executed. So these are just the things we showed, 1, 2, 3, 4, what's supposed to be done inside one of these workers, and the main thing is the run, which will be executed. And if you look at the run, you see that's how the run looks like. So the run is just creating the input, calling the execution of this external program that's doing the scientific calculation, and reads the output back. So that's what one of these threads is doing. And of course, this will be called 18,000 times. Yeah. This run will be called 18,000 times. So this is how this looks like, and I just gave it all the subtask names. It doesn't really matter what's inside. This is just details. There's nothing to do with threads. Only the run method is important here. And then that's the boss, so the guy, the main thread. The main thread is just a normal class here. So you can inherit from object, and if you're in Python 3, actually you don't have to. And this is doing a lot of preparation work. Everything that has to be done once. Like I generate the templates first, that will be filled later on. I generate some temporary files, directories actually, where each worker is putting files and reading the output from. It opens the HDF5 file. So I have open and init. You have to do something special with HDF5 to make it work here. In this case, you keep it open and close the HDF5 file. At the end, I read the parameters, the global parameters, and so on. And then the interesting part is actually this run all method. The run all method, it's doing the main work, and this is the only method that's concerned with threads. All the other ones are not concerned with threads, they do global tasks. So it's always a good idea when you work with threads to isolate this, whatever concerns a thread, in one method if possible. Then you know if something goes wrong with the thread, you only have to look at this one method. It might not always be possible, but in this case it's possible. So again, the burst is doing something that concerns the global thing, so everything that concerns all the 18,000 calculations you have to do. So I read the HDF5 output and write the HDF5 output. Theoretically, you could read in threads from the file, but I tried, it didn't work. So giving all these workers access to the HDF5 file to read separately, it didn't work. And I think it doesn't really matter that much, because when you read from the HDF5 file, typically the hard disk is the limiting factor anyway. So if 8 or 10 or 50 threads read from one file, it won't get any faster, because it doesn't come out any faster than the hard drive delivers it. So I have this main thread reading the data and writing it back. And I don't think it's a bottleneck, because typically the hard drive is a limiting factor to be fast enough. Well, HDF5 is a very fast way to read and write data, because it's a binary format. So typically the hard drive is limiting. So this is not a problem. Okay, and now how the communication works. I found this joke, I don't know if you understand, so for native speakers it might be understandable. So the patient asks, I feel like a billiard ball, and the doctor says, please go to the end of the queue. So we're using queues. So maybe somebody understands, otherwise I can give you a solution later. So we're using queues here to communicate, and that's what I would suggest you when you use threads. always try to use a queue for communication between workers and the main thread. Has a big advantage also if you later want to go to multiprocessing. Typically, you can move your code to multiprocessing, because multiprocessing uses a very similar model using queues for communication. Yeah, so that makes your life much easier. Don't, whenever you can, avoid shared structures of data where somebody's putting something in, somebody's taking out. Use a queue which is thread safe, and then somebody else solve the problem for you already. So, and the boss creates these workers. Typically, as many workers have CPUs, actually you can do more, I tried. And then I start a new thread, feeding it initial parameters, and then the most important thing, the thread doesn't have a return value, but rather puts a result in a queue. So that's how it looks like. See, this is this worker again, and now I show you the relevant paths for the thread. So I get a queue, every thread gets a queue. Then we see the run method again. Yeah? And then the important thing here, actually, it reads the result. You see this, these are these column names. We use pandas here to read the CSV, which is very, very convenient, actually. And then the important thing here, this is an important line, I put my result back in the queue. So I have an ID, so every thread gets a new ID, so I can tell them apart and just count up a counter. Yeah? And I put my output, which is a pandas data frame. And that's it. So there's no return, I put it there and then I'm done. I put it in the queue. That's how this communication works. And this is a main thread, and the main thread makes one queue. In this case, I use one queue. You can use different models, so it would make a different queue for each thread. That's also possible. I use one queue. And then I have a big loop here, and it's a bit involved here, but you don't understand everything. You see, I have IDs. I make as many IDs as I need to make simulations, and I try to get a next ID. And after a while, all the IDs will be used up, and then I get a stop iteration exception, and then I break out of the loop and stop the whole thing. Yeah, set down to true, which will break. Later on, we will see this. And now the important part is here, I make an instance of the worker, give it a queue, so that's the way the worker can put the result. And then I do a few checks down here. And here now it's unfortunately moved out. You see, I say queue_get, and queue_get gives me the result. So the queue actually asks, is there something? And that's what I'm doing. So as soon as something in the queue, I get something out and get the next result. And since I attach the ID to each of them, and the worker gives me back the ID, I know which result it is. So I use this ID. And that's pretty much it. Yeah. And then here, in the end, I've joined the worker, so I kill the thread. And here I also have two places actually where I get this get. This is just for some, yeah, that's at the very end. So this is in the main loop, and then when I get fewer and fewer, that's why I have a second get. So, but this is a communication. So the thread says put here, puts it in, and the main thread says get, and gets the result out. So no return value, but put and get. Very important. So queue is actually the way to go here. Okay, now, what did I gain? So how did it work out? So compared to doing a serial calculation where I just have one thread or one program without any threading, doing it one after the other. So I tested it on an Intel i5 thing with 8 cores. Actually, it's 4 CPUs, more or less, with hyper-threading. So I keep 8 CPUs busy around 90%. Which is pretty good. So you won't get much faster than, again, much more out of the 90%. And actually, amazingly, it scales up to 50 threads. So at first I thought if I have 8 cores or 4 CPUs, maybe 4 or 8 would be a good one, but I tried more, and even I got a bit faster using more. So the operating system somehow juggles those processes for me and is doing this. And 95% or so of time, or even more, is spent in external processes. So my program actually is doing very little computation compared to external processes, and I just need to feed them to get them run in parallel, and all the heavy lifting is done by the operating system because it's doing the threads for me. So that's what you want. You want to have the minimal effort and get other people doing the hard work. In this case, it's the operating system that's doing all the threads. I ran this on a Windows machine, the executes Windows, but it also runs actually on Mac or on Linux because I use Wine. So I didn't touch the executable, but I use Wine, and it works because it's just a GUI program, so I can run it on my Mac also. Yeah. Okay. So that's what I did. There could be other ways of solving this, so that's just my approach. So you can use concurrent features, which is a part of Python. So I haven't used it, I don't know even why I didn't use it, but you can use it. It gives you a bit higher level approach there. So this gives you a thread pool, and you don't have to handle it yourself. You could use multiprocessing, but I don't think that helps, because since most of the time is spent in external process, multiprocessing is starting even another external process, which the Python interpreter run. I don't gain anything here. But eventually you could move it to something on a cluster. So if you have a cluster and you would have, because I have 18,000 independent processes, I could theoretically scale it on a cluster with 18,000 cores. Would work something like this. And you could use something like Pyro4 or some other technology for this. So if you use Q, you're pretty close. You might have to change the flow a little bit, but you could use other technologies. But for our project, it was okay, because it was supposed to only run on a single computer. And 2.5 hours, the scientists are very happy with it. So typically they're used to something running overnight, and everything that's less than overnight, it's okay, fast enough. Good. Conclusions? Take-home message: use threads whenever you have input-output bound problems. The code, yes, you can see most of the code, it looks very much like serial. There's nothing special about threads, only those few places where I work with the queue. And try to isolate them in separate methods whenever it's possible. And whenever it's possible, also use queues for communication, which makes your life much simpler than using shared data structures. Okay, thank you very much. And there's a few minutes for questions, I guess.
So who has questions? In the back, of course.
Thanks for the presentation. My question is about thread safety. You mentioned there might be some issues, like what lines of your code could be changed so wrong things can happen?
Yeah, the main thing is if one of the sub-processes doesn't finish, yeah, then this thread would, this one worker would block. That could be a problem here. Yeah, so you need to have some timeout, which I don't have here now, to say if this one doesn't come back after 2 or 3 minutes, then you need to either restart it or at least make a red flag that it didn't work. In my case, everything was finished, so all the calculation finished, because it's a very simple statistical calculation, so there's no numerical problems that can happen. So I didn't have too much error handling if the sub-process dies. In terms of threads, since every worker is totally independent and doesn't interfere with the others, there shouldn't be a problem like a deadlock or anything, because nobody's really waiting. The only one who's waiting is the main thread for the worker to write a result. And if the worker never writes a result, it will wait forever. So in my case, it didn't happen, and we tried different versions. It works. If it would change, you would need to say, okay, ID 5350 didn't finish. Now somebody has to look what went wrong with this one. Or just, if you have 18,000, you lose 2 or 3, that might be okay.
Okay, any more questions? Okay.
My question is, can you make it possible to have multiple threads access the same data frame? So, for example, right there.
You can, but it's difficult because you have to do locking. So if you want to have multi-processes access the same data structure, can be done, but it can, because threads are not deterministic. You don't know at what time or when this thread or the other thread is active. The operating system is taking this over. So typically, I would recommend try to avoid it. It's possible, but it increases the level of complexity possibly 1 order of magnitude. So make it as simple as possible. If you want to do this, just like if you have an array and you have a shared array, just say, okay, you have 4 threads, subdivide your array in 4, and this thread is working this part and this part, so they don't interfere with each other, if possible. Yeah? Otherwise, you need to lock and say, now I'm doing something, and if you lock something, you have the potential for deadlock. And it's very difficult to debug, because it might never happen, because it only happens once in 1,000 times. And it's really hard, because you cannot reproduce this. And if you're going to reproduce this, you cannot debug it. So try to avoid shared data structures whenever possible. If you really need something in parallel, and you do some computational heavy things, you might want to look at some other technologies anyway, like OpenMP or something with Cython or other parallel technologies. Then Python threads might not be the way to go. That's my recommendation.
My question is regarding the bottleneck. Is there a specific reason why you didn't use a database? So in order to avoid the bottleneck of writing to one file and having a database?
Actually, HDF5 is very close to a database. It's designed for scientific data, and there are a lot of benchmarks. Thus, HDF5 is, for a lot of use cases, faster than Postgres for reading and writing. You can also, the thing is, if you look at it, I spent 95% of the time in the external process. There's a little bit of reading and writing, it's just maybe 1% of the time. So even if I make it twice as fast, I go from 1% to 0.5%. It doesn't make any sense. You want to spend, most of the time is spent as an external process I cannot change anyway. So the performance only becomes because I don't wait to finish one process or the other. I run 50 of them in parallel. And that's where the time comes from. So the writing and reading to the file is not the bottleneck, because the database also has to write it to the hard drive, eventually, or the SSD. So this would be, the physical writing would be the limiting factor. But in this case, it doesn't really matter because this external process is dominating by far.
Okay, any more questions?
Here's one more here.
Ah, I didn't see you.
Hello, thank you for the talk, it was awesome. Regarding reading the file, as it was so big, you were reading it all at the same time, or you were reading a chunk, feeding it to a worker each time?
Yeah, no, I have one big file with all the data, so HDF5 file, yeah, and I only have the main thread accessing the file. The workers never access any of this main file. They do generate intermediate files for the external program. So this XML file and this CSV files are generated by each worker. Yeah, and then because the external program needs physical files, yeah, so they generate these input files. They're pretty small, 9,000 lines is not a lot. Yeah. And then the external program reads them and writes an output, and then the worker reads the output and changes into a data frame, and hence the data frame back to the main thread, and the main thread eventually writes this in a big HDF5 file. I end up with a HDF5 file with 132 million lines, and then I need to rearrange them, which HDF5 is doing because you can index HDF5, and it's doing all the sorting for me. So I don't have to load everything in memory. I can index it, and it's sorting this, and it takes about half an hour to sort 132 million lines, which is pretty good.
Thank you.
Okay, anyone else? Ah, I have to run today.
What do you think about using greenlets instead of threads for the same problem?
Can you repeat it?
What do you think about using greenlets instead of threads?
Greenlets,
yeah.
I think it would be could also be done. There could be many approaches. You could use async programming if you want. You can use greenlets, but if you use greenlets on async, you need a reactor. You need to totally change the way. Here, you can mainly use serial code as you would write a normal Python, and only these few things you have when you work with this. You have to inherit from thread, then you have the run method, and you have the queue with the get and put, and that's pretty much it. Yep. Yeah, so it's a different thing. So typically, asynchronous programming can be much faster if you have hundreds of thousands of things going on at the same time. Then threads is probably not the way to go. But here, if I have 8 CPUs, typically I don't have more than 8 things going on at the same time, so threads are perfectly fine. So having a few thousand or 10,000 threads for nowadays computers shouldn't be a problem. If you want, you can run a million. With async, I know probably you can easily run a million things at the same time. It's a bit different task. Yeah. So, but you could use greenlets, you can use async, you can use many different approaches. It just depends on your preferences, what you know already, and what's available. Here I don't need an external library, and I think from my imagination it's pretty easy to follow what's happening. If you have greenlets, you have to learn how they work. But it's certainly possible.
Okay. Anyone else? No? Okay, then thanks, Mike. Give him an applause. And please remember, you can rate these talks in the app. The organizers would be very thankful for that. So do that. Okay, hello everyone. Our next speaker, Sebastian, he will have to speak about why we don't need design patterns in Python. So give him a big welcome.
Hi everyone. I want to tell you a little story. Of course, not about myself. It will be a story of a Python developer. Not so long ago, there was a Python developer, and throughout his career that lasted already several years, he wrote a few thousands of lines of code. And he was in love with his favorite framework, and he became so proficient in the tools he used daily that he even became a mentor for his teammates. And he praised all the tools he used because they were able to solve all his problems he dealt with in daily work. And after all, he was quite good. And this really boosted his self-confidence, and this isn't surprising. Of course, knowing a framework was not his only asset. He practiced writing tests rigorously and applied TDD whenever it was applicable. He was doing his best to make sure that the code he written was not only correct and well-tested, but also readable and easy to understand by any other teammates. And every night before falling asleep, he was reading a Zen of Python to write a code that would never violate any of its verses. In other words, he was doing his best, and he was expecting the other teammates to do the same thing. And then he was assigned to a new project that changed everything. Well, despite the fact that our hero was proficient with his tools and he knew them inside out, they were not well suited for the project he was assigned to, because how valuable this experience may be when the weight of the project, its very business part, is far outside this framework. And it can no longer be solved by this framework, essentially. So he started to create his own classes, his own modules, and his own abstractions. And he felt that they were clumsy and they do not be as good as the well-thought components of a framework he used daily. You see, frameworks are sets of powerful building blocks. If you use them for problems that they were created for, you're fine, and you shouldn't bother any other options. But the problem arises when there is an issue that they simply don't fit, and you try to, effectively screw driving using a hammer. And for example, what would be the Django good for if you did not need to use its models at all? So what's left? I don't know, the views, the template system, and the routing, and that's all. Any other rich capabilities of Django are not used, so why would you do that? And the problem why our developer was stuck was that he lacked the thinking outside the box, beyond his manual. And luckily, he noted this problem early enough to come up with an idea of asking someone maybe more experienced, maybe more interested in software engineering. And he had a friend, a Java developer, and he asked her for an advice. What should I do if my tools are not good enough for me, for this particular problem? And she said, take a look at design patterns. They are meant to be reusable concepts to produce elegant code and nice solutions, and are based on many years of experience, people that are much smarter than we are. So our hero took the design patterns, took the 23 years old book, and tried to implement some of those using examples there. However, the design patterns are not like libraries or tools that he dealt so far, so they are not easy to use solutions that you just import in your code and start using. They are more like recipes, like drafts for solutions. If you have this particular problem and they fit, like you have analogy, then you can use them. but they are just outlines. They are not ready to use. Maybe you are thinking, what are they good for you if they are written in some old books by some C++ guys? Well, there's a funny fact about IT, namely our brand has some kind of amnesia any 20 or 30 years or so. We forgot about old concepts, old ideas, and then we discover them again, and we're like, oh my God, this is so amazing. Cool. For example, let's take an async IO and its coroutines, yeah? Cool idea, the event loop. Except it's nothing new because this is almost 50 years old now, and this has been around in the 70s. But we just now got it to the Python. And another thing to consider when you think about patterns is that are they applicable today? And well, the book was written 23 years ago, which there were different tools in charge instead of Python. So Python simplifies a lot of things, and this is what this talk will be about, more about the tools and less about the design patterns, because you will see that some of them are also present in Python, but they are invisible, or you cannot differentiate one from another, because they are so simple. But the main benefit from design patterns, or at least learning their application in Python in some limited way, would be for you to extend your toolbox as a programmer, and as a result, become not only a better Python programmer, but a better programmer in general. Okay, so let's start with the first pattern. There is sometimes considered an anti-pattern, a singleton. This is a situation when you have a class, and in any moment of lifetime of a program, you need only one instance of a given class. Only one object has sense. There may be several reasons for that. Maybe all the objects will be the same, so why should I bother and why create new things every time? And maybe there is a business motivation behind this, that there would be no more than one object. Or maybe creating an object costs a lot, takes a lot of time, and you just want to avoid it to get some speed up. And for such cases, we can use a singleton pattern. And beside uniqueness, there is also one requirement. Namely, you need to have a clear way to get an instance and know that this is a singleton. So after Googling a little, you may find the following solution. And this uses a magic dunder new method that is using during creation. So this solution comes down to using a class level attribute that will store your only instance and eventually return this whenever it's necessary. Using this is quite simple. You just create as usual as you would like to create the other object. And of course you can use this implementation in your programs, but please don't call yourself Pythonistas anymore. Because, you know, there is one very serious flaw, I can see this, and this is that it's not clear for a client of this class if he creates a singleton, if it's really a unique object, because we use unusual syntax for creating a new object. So you might get surprised if that you really getting is the same thing over and over again. A slightly better approach is to use a class method. A class method has this advantage that this is more clear, and it also does not block you from creating an unusual instance. Well, you could do the same by clearing that class level instance variable, but we don't want to go that far. However, since we have Python and it's 2017, there is a simpler way, and actually it's been around in Python for several years, I guess, or more. And this is, you can just create an instance object in your module, and later in your code, just import the object instead of class. And this will achieve actually the same thing. So I told you that some patterns are present in Python, and this is true about singleton. This is not an obvious fact. but there is a creature in Python that you use it countless times and actually meets the requirements for singleton. And this creature is called a module. So let's consider this. After importing a module at least once, there is exactly one instance of it in sysmodules dict object. You can very easy and very clearly get an instance of a module using import statement. And if you need, you can recreate the instance using reload. So this actually adds something to this pattern. So the conclusion about singleton is that using the most simplest solutions would be your way out instead of creating some clumsy classes. And if I'm speaking about modules, there is another pattern that very gets simplified thanks to them, and this is facade. Let's say we have a project that is consisting of many distinct components, and we can quite easily assign them to some groups responsible for certain functionalities. For example, we have a group with users that is responsible for getting user, authentication, and so on. We have a group responsible for blog posts, creation, retrieving, and other stuff. And we have some things related to getting advertisements based on the contents. A net of connection between these classes might look like this. And I don't have to tell you that this is a terrible idea, because you get a tight coupling between these classes. And anytime you want to change something in a class that has many connections with others, then there is a probability that you will break things. And also, it's very complicated to get a desired functionality because you may not know what's behind this subsystem. Yeah? And this is what facades, this is issue what facade tries to address. You introduce in your original pattern an extra class that will be your interface to the entire submodule. You are no longer allowed to use these classes directly, under no circumstances. All requests that go to this subsystem must go through the facade. And of course, you can go on with default implementation, like using class methods all over and creating another class. But perhaps this is an over-engineered solution in Python, if all you need is just a top-level package that will get a bunch of functions inside. Just look how clear it looks compared to the idea of modules. The only thing you use outside this package is imports from this init file. Everything that's in these sub-packages is hidden. You may not use it outside. And this is how you hide the complexity of probably very complicated advertisement subsystem. So this pattern it doesn't sound like very original or something, but it helps you organize your code. And there is very little need for class in Python if you can do this the same in plain module. Another pattern is a command. A command is an object-oriented callback. The original implementation assumed that it will be helpful, for example, doing graphical user interfaces. Because you see, when you want, for example, have a reaction on clicking an item in the menu, you don't want to pass too many information to the graphical interface with the same reasons as the facade. So you don't want to have too many connections in your system. And the command was meant to pass and configure during runtime your things. Its interface assumed that you have only one method, which is execute. And the thing that uses command would just run execute when it needs to. Of course, in Python, it's over-engineered because we can use just a plain function to achieve the same thing. And since functions are first-class citizens in Python, which means that we can create a function during runtime, we can pass it to another function, and we can return it, then there is no need to create a class. But I remind you, these were quite different times where the basic building block was class, so you have classes everywhere. And if everything that your command is doing is just calling another functions of another object with some parameters, then maybe you can use the standard libraries goodies, which is functools partial. And this one allows you to just prepare a callable object that will be accessible later to use. But in conclusion, we do rarely stuff like this in Python, which making graphical user interfaces. So this is a pattern of very little usage in Python right now. And another pattern is a visitor. And this is actually adopted in Python, and it's used, but for a certain amount of problems. Let's say we have a complicated nested structure that we need to traverse, and for each such node, we would like to execute our own logic. And this is an example of abstract syntax trees. And this is your code represented as such structure. And this is really use of PyLint and other linters, which get your code, turn them into such structure, and then per each node does distinct logic. For example, a root element is always a module, and this is represent the whole code. The first thing you have, this is import statement, and this is represented as distinct node, yeah? And PyLint has different checkers, different strategies, different guidelines for any of these elements. So it is much more clear to just separate this. And this is what visitor is about. It's about getting to know what is this node and separating this parsing from others. If we had a static typing, just like in Java, then we could just implement it like this. We would have a method visit, and the arguments would point us what type is this implementation about. Yeah, we get a clear distinction about what to do next. Of course, we don't have such things in Python, and the first naive implementation will amount to using big if-elif statements, which I don't have to add to you that this is ugly, and this grows quickly, and it's slow. Luckily, we can use the dynamic nature of Python and create functions that we will call them later as usual methods. After we assemble a method's name, we can just get it from our object and call it just as usual function. And this will work fine too. But having Python at least having at least Python 3.4, we have this single dispatch functionality, which this is the closest what we can get comparing to Java. So it's directing implementations per argument type. Its usage is quite complicated. I will get it step by step. So first of all, we implement the single dispatch, and we get a default implementation. Of course, the default, if we did not have a specialized version for this time, we will want to raise exception that this no handler is for this thing. Then we would start implementing our all specialized implementations using, take a look at this decorator, because we don't use single dispatch, we use the visit decorator.register. And this decorator gets the only argument, which is a type of a first argument to this function. And whenever you call a visit with a type, like in this place, then this registered function will be called. Unluckily, this has a major disadvantage, and namely it cannot be used in classes, because there's always a first argument is a class. It would have to be re-implemented by hand in such case. Okay, and the last design pattern is decorator. And decorator pattern is not what you might think of when you hear a word decorator. It's not a decorator function in Python. It will become more clear when I will show in examples. And now, some requirements. It can extend the behavior of a given object during runtime, and it can be used multiple times with different decorator patterns, and no order is not important. They should work the same way, or at least have a meaning desired. So a decorator, when you decorate an object, you have to get the same thing back, which means as a user of class, you shouldn't be aware that this uses a decorator. So if there is any attribute on the object, then it should be also present on a decorator. And for example, if we have such class that has two methods, getText and getNumber, and we would like to decorate one of them by adding some bold HTML markup, then we have also to re-implement the other function, which is of course redundant, and this is just writing a code for art, not for making functionalities. But what happens actually if we request an attribute on a class and we use the dat? The methods on classes and its fields are just attributes, and this is a logic we can plug in. So first at all, Python calls a special dunderGetAttribute method, and this looks for properties in the object itself. If it wasn't found, then dunderGetAttr, I know, wonderful naming, is called, and by default it just raises an exception that this property was not found. And looking for properties is by dictionaries that are per class and per object level. Okay, if the same property is present on class and on object, then an object has priority. So to get decorator simplified, we can just implement the method we need, and for any other thing, we just return the stuff from the original object. And this frees you from need to implement all this unnecessary stuff. Okay. To get a full compatibility, you would also have to implement the other methods, but that's a different story, I guess. So, to sum up, Python is a very flexible tool, much different from what we have almost 25 years ago. And many of these things you might think are either redundant or extra art just for it. But in Python, there are multiple places when we can plug in our own logic and customize on nearly every aspect of creation objects to runtime. However, the very important question arises: is magic that I showed you in some limited way is worth the effort? Should we use really the magic? Well, it depends. The readability wins. There are cases when using this stuff will spare you some effort, and any other things that would just create, I don't know, I see a fancy Python feature, let's use it, it's a probably wrong idea. And there are three things from me that I want you to take from this presentation to become a better programmers in general. So first of all, get to know with your tools and know them well. And this is like vocabulary, like having a name for everything you see. The second way is to get inspiration from other languages and communities, because there is not much interest in Python community in general in software engineering. There is not much talks on this subject on conferences. There is not much books. And the last thing I haven't spoken earlier is to know a business domain of your project. Because if you know your tools, you have a vocabulary. If you get inspiration from the languages, you know the software engineering stuff, you have a grammar. But a real value, a real meaning, what you do is in this point. So even if you write a beautiful code and know all the tricks, and you still won't be able to solve the problems of your business, of a company you work for, then this is all for nothing. And just to sum up, my name is Sebastian Buczyński. I work for STX Next, the biggest software Python house in Europe. I blog under breadcrumbs collector.tech. And that's all, folks.
Okay, we have time for about 2 to 3 quick questions. So, who has a quick question? Anyone? No, everyone has hungry. There is one.
So it's less of a question, but more asking for a comment of you, because in my opinion, actually, I come from the Java development community, and design patterns are really important, and I also realize they're really important in Python. For example, the facade pattern you mentioned. Sorry, I will keep it short. But my question for your comment is, you said that design patterns are not really important in Python, but of the 23 patterns in the Gang of 4 book, sorry. Like, are they actually really not important, or are they important to implement sometimes, or just forget about them? So what's your opinion on the design patterns and their importance in Python?
I need you to repeat the last one, because sorry.
Okay, so, I mean, your title was design patterns are not important in Python. But honestly, is it important to learn these and then implement them? Or, I'm sorry, I can't really make my question.
Okay, so your question was about, is it worth to learn the... Okay, so essentially, I think that this is a tricky part for less experienced people, yeah, because they learn unnecessary stuff. There is a gap in our community, yeah, and this is an established set of well-thought best practices. I think this should be prepared by someone, maybe, and this should be well propagated throughout the community. So they do not have to learn from from 23-year-old books, yeah, because they are not relevant today. So we need just a new set and counterpart for Python.
Okay, anyone has a question? One more question? No? Well, then it's time for lunch, I would say. Give him a hand.
Thank you.
And please try to rate these talks in the app. I was
Welcome to the afternoon session. Our first talk will be by Sebastian Neubauer, who works with Blue Yonder as a senior data scientist. And he will tell us how to bring, that there should be one obvious way to bring Python to production. Give him a warm welcome.
Thank you. Welcome. I'm really glad so many people here. Maybe some wanted to see the Facebook talk, then you are in the wrong room, so maybe you have to switch. If you're really here for that talk, I'm really glad. Thank you. So, yeah, it's a long title, and so a brief agenda, what we want to do today. So first of all, we have to settle some of the definitions. So I want to give you a brief overview of things like what is a delivery pipeline, what I understand about this, about dependencies, maybe some packaging. And then I want to do a small walkthrough through the different possibilities of how to bring Python into production. And I will also give some pros and cons. Yeah, and in the end, I mean, all of you, of course, want to know the one question, so what is the obvious way? So, yeah, first of all, I want to give some insights, I think, what the future might look like. This is my very personal point of view, but yeah, it's difficult to do predictions for the future. We all know this. And then I want to do a small discussion. So I want to know what you think, what the one and obvious way should be. Okay, so what are we talking about and why? So here I have a small picture, just sketching out what a thing is, what we call delivery pipeline. So who here has heard of this word before? Yeah, some of you. Okay, so yeah, so it means how do we bring things we develop in the end into production, which means we deliver something to our customers, whoever it be, whatever it will be, it doesn't matter. And here we have some stages, and I will go through these stages. So there's development, some building, packaging, testing, staging, Q&A, and then in the end it hits production. Of course, not each of these single steps is always present in each project. There are small projects, maybe they don't have any Q&A, but that's more or less the general view how such a pipeline looks like. Okay, so let's start. We start in the beginning, also how a normal delivery looks like. We start in development. So we have some requirements there. We all know most of you are developers, I think, so we know what we want to have in our development stage. So we want to have fast iteration cycles, we want to change something and then immediately get some feedback on whether it's good or bad. And I would say that's a hard requirement. We need to be able to run our automated tests in our development environment. Maybe not all of them, but at least we all notice some unit tests, things like this, so yeah. Maybe a nice to have thing is that we have some kind of an emulation like the production system. So maybe we are able to start our Flask server or things like this, or maybe we have a small Postgres running like in production. So, but this is already a nice to have. For some projects it will just not be possible to really have a production-like system on your laptop. And we also have some risks here. So we all know this. Oh, what happened? It works on my machine. So this is the typical problem we all have on the developer's box. Everything looked fine, but in the end, production breaks. And this also happened to all of you, I think. So everything went really well, but we forget to commit the very important file. So in production, it is missing. So this is also, we have some kind of a dirty working directory. Okay. So then the next stage would be building and packaging. So of course, you would say something like Python, we don't have a compiler, but that's not true. So there are extensions, Python extensions, things like this. So in general, there will always be some kind of step where we do a compilation of things. So we build our artifact. what would be required here? So I would say a very good best practice is we want to build this artifact just once and then use it everywhere. Yeah, there should be also, of course, there should be a possibility to compile for our target system, which means mostly the production system, but also maybe for the target system. So we need some kind of, so either our build environment is really similar, or at best it's really equal, or at least we have to find some ways to do cross-compiling or whatever. And another thing is, if we want, if we have an artifact and it has a version, it should be unique. So if someone in the company says, I have version 1.02, it should be really unique thing. There should never ever somewhere a tar file or whatever with the same version, but in the one there was this one config item missing, and in the other one we compiled it in. This should never happen. So this should be just unique. And I would say that's purely required. If this is not the case, then you should at least think of how you can get there in the near future. Then here the nice to have is something like an artifact repository. For Python, maybe there is DevPy, or there's Artifactory, Nexus, whatever it is. So it means we have a server where we can put our artifacts, and everyone in the company can just pull off these artifacts which we build in this build step. Of course, the risks here, if we have this artifact built, it might, of course, be that there are bugs, so maybe there's some misconfiguration, maybe we have some dependencies missing, whatever. So this is the risk what we have here. So the next step, testing. So we could argue maybe testing comes before building the artifact, or maybe some other ways, but I would say in principle, because we want to use the artifact and test this artifact, it should be after the build step. So what is required here? It should be automated, and we heard this in the talk of Martelli with the testing layers. So tests that are not running automatically, we don't call it test, we call it another development step maybe, or whatever. So if it's just someone saying, I clicked through it and it looked good, this is not a test, this is something else, but it's not a test. The conditions in these tests, they should be as near to production as possible, and I mean, that's clear. So in the end, we want to test if production will work out or if it breaks, so it should be just very similar. We want to have reproducible conditions there, so not that at 12 o'clock it fails, but on 1 o'clock it works again, just because there is some condition changing. And that's more or less the quantum mechanical thing, so maybe you know Schrödinger's cat. If we measure something, if we test something, we always interact with the system, but these interactions, these changes we do in our thing we want to test, they should be as minimal as possible. So for example, a thing here is that you install PyTest, and PyTest brings in a requirement which is in the end missing in production because you didn't write it into your requirements file, because in the test it was present because PyTest installed it. But in production we don't have PyTest installed, so it breaks. This would be a change which is happening just because we tested. Then here, nice to have, it should be as fast as possible, just that if we commit a change, we want to have as fast feedback, it breaks or it doesn't break. But of course, there are tests that run maybe for several hours just because it's a matter of fact. Then it should be as fast as possible. And also nice to have if we are able to really test all the tests we have for all commits, not even just on master, but maybe if we have feature branches or even short-lived branches, we test on every branch, or pull requests or whatever. The risks here, of course, I mean, it's hard to read. The tests test the test environment, but not production. I mean, that's obviously the thing. So, yeah. We know a pretty famous example of this, the the VW Dieselgate thing was exactly this. So the test was measuring that the test has the right conditions, but in production it's a complete different thing. So this is exactly what is here. Maybe we don't want to do it in purpose, like some people in VW, but it might happen. Okay, so the last step here, before we hit production, is some staging or quality assurance requirements. Here we have an automated deploy, so this is now the different. We really test how we install it on our target systems, and it should be really a production-like system. And we don't want to have any changes for this staging. So for example, with the PyTest example, in this stage, we do not want to have PyTest installed on this Q&A system. So it should be really a production-like deploy. And nice to have here, if we can afford it, we just have a real one-to-one clone of the production system. If we are able to afford it, good. If not, maybe it's good enough to have some smaller servers, smaller databases, but in the end, it should be really as production-like. If we have a real production-like system, then we also would have the possibility, for example, to do A/B tests. So that, for example, 10% of our customers already hit this new Q&A systems because that's the best test we can have. So we then are pretty sure it works for everyone if it works for 10% of our customers, but the risk is very small. It just hits 10% of our customers and not 100. The risks here, maybe that's not so critical anymore. We have cloud, we have things like this, but 10 years ago, these systems were always purely maintained. There were things like, oh, we forgot to update the last database migrations, and it's running a very old MariaDB, and it's not really working. We don't have installed all the dependencies there. So this, of course, should not happen. So it should really be as good maintained as the real production system. Because in the end, it's part of this value stream, what we do, development and so on. So there's really we cannot afford to say, okay, it's just the staging system. If it's red, it's not that bad. That should not happen. Okay, then we hit production. So here are some hard requirements. I know that some of them might not be present for everyone of you who is running a production system, but I would say same thing here. Maybe you should fix it as soon as possible. No compiler in production. This is just a matter of fact. So we cannot afford it. It's a security nightmare. There is no compiler. No internet at all. So there is no point in reaching PyPy, whatever. This might be the hardest thing, but I mean, we can just say this is a requirement, and if we can afford it to have it, then it's really nice. We exclude a whole bunch of security issues and some kind of health monitoring. So nice to have here that the deploy is automated. In the meanwhile, it's happening everywhere. Everyone is using Ansible, things like this, but it was not 10 years ago. Automatic monitoring. Maybe it's possible to have some infrastructure which automatically monitors some of the health checks, some automatic self-healing, which would mean, okay, if one thing goes down, it automatically gets rescheduled and comes up again. And maybe, so this would be really the best thing, have some rolling updates, which means we have a new version and we don't have to schedule a downtime and bring down the whole stuff, deploy the new version and bring it up, but we can maybe start with one server, then the next, so a zero-down upgrade. And if we, in this process, find some issues, we can just do a rollback, and we are just there where we were at the beginning of our update. The risk here, it's pretty simple. Your business is going down. Maybe it's even fatal, so you will not recover anymore, and you are out of business. Maybe that's the most extreme one, but this really is production, so we cannot afford any failure there. Okay, so now I scheduled maybe some, let's say, good setup. Maybe it's not the best in the world, but I would say this is something which would be seen as good. So we have our normal developer's box, so a laptop or whatever. For the building, packaging, and testing stuff, maybe the staging. So this is more or less not so clear. We have some kind of continuous integration server, Jenkins, whatever, you name it, Travis. And then in production, it would be good to have some kind of modern cluster scheduler. So not just some hosts which can go down and things, but maybe some Mesos cluster or whatever. So because there we can get things like rolling updates for free because they implemented it already, so we don't have to care for it. It's just implemented already. Maybe a bad setup, but I think most of you already seen some of those setups. So you just develop and build everything on your computer, and in the end, production means you have some server on rack space which is 2 years old, and you installed with some sudo apt-get things you can't remember. This happens. For example, for some hobby project, I think this is completely okay. If it goes down, it doesn't matter. But for your production system, I think this would be a bad setup. Okay, dependencies. So that's my definition. I made it up. All shared software components that need to be present in the correct version so that the application works correctly. Okay, maybe we can work with this, so this means somehow software needs to be present. But there's a thing called dependency hell. It's pretty famous because normally you screw up these kinds of things always. For example, you can have those conflicts in transitive dependencies. So A depends on B and C on D in different versions, so you cannot really resolve it. Then there's another issue. Armin Ronacher brought it up also in the keynote. In Python, we only have application global dependencies. That means if Flask depends on something, I cannot depend on this in another version. This is possible in JavaScript or maybe some other languages, but at the moment it's not possible in Python. So we all have to agree in the whole application on one version of a dependency. Pip, that's a sad story, of course, we all know it, still doesn't have really a proper dependency resolution. All it does is it takes the first one which comes, fulfills the first requirement, and it just takes this one. But, so there is an issue, number 988. It's some years old, 4 years old. But the last comment there is that this year there's a Google Summer of Code project, and a student gets paid to implement this in pip. So fingers crossed, maybe we will have some proper dependency resolution as far as it can get, because still it's global dependencies and there are just unresolvable problems. This is another thing. We have this system Python dependencies. For example, Debian comes normally with a pip installed. Who knows which version pip is on Jessie? No one? It's 1.5.6, so it's really, really old. The newest one is 9. There were some steps missing in between, but still it's a really, really old pip version. So if you just want to install something in Python on a Debian Jessie, which is not the very newest, but the last stable one, or in the meanwhile, it's not the last stable one, but it's still fully maintained. It's really a hard time, because you have to upgrade the system pip, and this crashes maybe everything if you do not really take care what you do there. Okay, then the next thing, package management. So how do we manage those dependencies? So in the Python world, I think we all agreed. In the meanwhile, there's one package manager called pip, and that's it. There's one package format, there's this wheel. But still, there is quite some, I feel there's quite some confusion around. There's still setup tools used quite often. There's still distutil stuff used somewhere. I find always some X lying around in my working directory, and I have no clue where they are coming from, but they exist. So it's really a sad story, and if you look up some how should I install this package? Also in Stack Overflow, they are quite outdated sometimes, so they would propose things like setup tools or things like this, and yeah, so it's still not really throughout the whole language environment universe that pip and wheel is the standard and there's nothing else. Also templating, so here's the developer of PyScaffold. Wave your hand. Hello. But there's no standard one. So if we want to set up a package, a Python package, it's still really pain in the ass to really set it up. So what do I have to write in my setup Py? How do I get Swings documentation built automatically, things like this. So there's PyScaffold or Versiony, or I think yesterday in the Lightning talk there was another one. Yeah, okay, so I have to be a bit faster. It's gotten better. Now we have setup config and setup tools SCM, things like this. So it's gotten better, but it's not really good. Okay, maybe okay. There is one big problem, and this is we have the whole world of system dependencies managed by things like Yum or apt-get, and there are the language dependencies. And this is not only a problem of Python at all. It's throughout the whole IT. Thing. So there is NPM for JavaScript, there is Conan for C++, things like this. So every language comes with its own package management for the language packages, but they somehow interfere with the system packages, and they rely on some system packages to be installed, things like this. So it's a huge problem. I think it comes from this DevOps problem. So we had the big division between operations people, and they manage the system dependencies, and then we have the developers, and they care for their dependencies in their own language. And still we have this chasm, and so I see no real movement that we really want to break it up. It's gotten better, but there is this problem. So I would say this is a fail. We have to fix it somehow, but there's nothing really inside. Yeah, so as I explained already, I think so there are some historical reasons for it. Why do we have dependencies at all? This is, yeah, maybe disk space was expensive, so it's better to share some shared artifacts. So we install, let's say, glibc just once and not 20 times for each application running. So these are the things why we have this chasm. So what is the current state? So I don't have too much time left, so we have to go through it quite fast. So now I have some approaches that we can do. For example, there would be the classical approach. So we start developing, then we build a normal package. So this is the classical approach. So I think all of you would agree that this is more or less what you would come up. So we build a normal package, then we push it to Git. On Jenkins, we build some artifacts. This means we build our wheel, we test this, and then we release it maybe to a DevPy server, and then our wheel is up there or on the upstream PyPy server. And then in production, we just go to our repository and grab this artifact with the version. So this is the classical approach. So the pro side here is this is the standard thing. Everyone understands how it works. We have good tooling around. We can use pip. We can just use all standard tools, and it's really well understood. The cons maybe is we have to resolve the dependencies in production. This might be a problem. Yeah, and we have to build those wheels for all target systems. So if we have some CentOS or some Debian, then we have to build it for Debian and for CentOS. Then there is this approach. We somehow conserve our virtual environment. There are many of those implementations. Oh, just 1 minute left. Okay. So for example, there's Flutter or PEX or DH virtual env. So the principal idea is we just pack the virtual env together and ship the whole tar file, and then we just extract the tar file in production. So yeah, the biggest pros on this side are we don't have to resolve the dependencies on the target system. The The con side here is we still don't have the system dependencies, it's just the Python dependencies, so we still have to have installed all glibcs in the right version or NumPy, LXML, whatever. Then there's the OS package approach, so I think you all can imagine, so we build Debian packages, for example, proper Debian packages. The biggest drawback here is, of course, that we need to package all dependencies we have as Debian packages, and it's a it's a huge amount of work. Then, of course, we all know there is Docker, and this solves everything. It does not. What I here want to address is containers as package management. So if you just use Docker, it's not the same like if you use Docker as package management, which means you build your Docker file once, put it to an artifact repository, and then grab this image in production as your artifact. If you just use Docker on your laptop and then you rebuild your image on production, it's not containers as package managers. I mean, there are of course some pros because you can use the same image everywhere, and it doesn't matter which host OS system you have. But still, we have some huge problems. For example, we still have the division between system and language packages. It doesn't go away. You have to install things in your Docker image with apt-get and then switch to pip or whatever, however you do it. Security is a huge issue. If someone updates the shell shock vulnerability on the host system, it doesn't care because it's still running in your container. So somehow someone needs to fix all the updates there. And then there is another thing, I would call it the next package manager. For example, there's Conda, you all know it, and this means, okay, we just invent a whole new thing. It's not pip, it's not apt-get. We invent another package manager, and they are taking care of already pre-compiling all the dependencies. So another thing here would be maybe Nix. Who has heard of Nix? Oh, some of you? Okay. It's a complete new thing, and I think this is the first time this would solve this chasm between system dependencies and language dependencies. So this would be a complete language agnostic approach. We can use JavaScript and other packages, but it would go down directly to the kernel. So if we then install something with Nix, we can, we all have, everything is installed, and of course there, the good thing is if we then update a system dependency, it would be really in our application. So this whole Nix takes care that our application gets restarted, things like this. A last thing, but yeah, okay, I have to stop. This would be the Google approach. You just take the package and download the source code and put it in your source code. The good thing there is you don't need the dependency resolution. It's everything just in your source code. But of course, you all know the bad things there. You would just screw it up. Okay, so that's it. So the future, who knows? Thank you.
Thank you very much. Thank you very much for a nice talk. We have time for one or two very quick questions.
So on the Linux side, there's new kinds of packaging formats are coming out, which include flat. Okay, so on Linux, there's these new package formats designed for this problem, which are called Flatpak, and then there's another one called Snap. So do you have any experience with those, and how would they tie into this?
No, sorry, I don't know.
Thanks, it was a good talk. Instead of a short discussion, do you have a brief opinion?
Yeah, so of course I thought a bit about what could be a solution to all that, and so I mean, the first thing I wrote here is containers will stay, so they won't go away, and I think it's a good thing. So containers will stay. We have those image formats, but I think we have to break up the division between system and language dependency. So I'm pretty sure we would need one language agnostic, so it doesn't matter if it's JavaScript or C++, one package management which can resolve dependencies and goes down deeply until the kernel. And so maybe there are some, so the nearest thing there would be using NICs inside a container. That could be a solution which might work out. But yeah, I think it would take some years to get it through so yeah, I don't know. But that would be maybe my shot.
Okay, so with this outlook, let's thank Sebastian again for his talk. And please all remember to use the conference app to rate the talk and give some feedback to the speaker and to the organizers.
And good rates.
about testing at SAP, especially how they use Python to test SAP HANA. Give him a warm welcome.
Hello, everyone. So, first about me. So, my name is Christoph. I'm working in the QA department of our in-memory database, SAP HANA. And this talk will show you very, very short introduction about HANA itself, because it's important for the rest of the talk, and then about how we are using Python to test SAP HANA itself. So let's get started with SAP HANA. It's a relative new product of SAP. It's an in-memory database, which means we have some storage engines, a column store and a row store, which is really optimized to run in the main memory of a system, of a server. And with the optimized algorithm, it's much faster to find things, to perform queries, and so on. And it fits very well for online analytic processing, so you can do normal analytic queries on it, or you can also use it for transactional processing. A typical database, you install it maybe on just one system, but we can also build up a scale-out system, so you have multiple nodes and connect each other to build a big database, and then you can distribute your tables across the systems and so on. For you as a Python developer, it's actually not so interesting, because your interface is most of the time just SQL, and then you use the database. So it's basically not so interesting about the very detailed insights, but who knows. So HANA itself is written in C++, so not so interesting for us. But we deliver a lot of management tools and commands which are totally written in Python. And one part of the HANA distribution itself is also a Python interpreter. So I told SAP HANA is an in-memory database, which means you need a lot of memory. But you can start from the beginning. So we have, for example, one small Express edition. You can start with it on your local notebook. You just need 16 gigabytes of memory, but you can also scale out and have a system with something like 48 terabyte of memory. And there are real customers which are running such systems, and it's still very impressive. So if you take a look how you can use SAP HANA, or you can connect your Python application with SAP HANA, it's very straightforward and very simple. We have a Python client since basically the beginning of the time. With the next service package from HANA itself, the Python client will be fully supported and has also support of Python 2.7 and Python 3. And then you interact with it over the typical DP-RP interface. So you open a connection, open a cursor, run some SQL, and you can fetch result. But as most of the Python developer doesn't write SQL anymore, and personally I can totally understand this, we have also some open source projects, or basically there are open source projects, to interact with the database. So there's one dialect for SQL Alchemy. You can run SQL Alchemy very easy with HANA, and it makes a lot of more fun than writing SQL. Or there's also another open source project to use SAP HANA as a data backend for Django itself. So let's talk a little bit about testing a database. Testing a database is not so different to testing a software, because database is just a software. So we have this very typical pyramid. On the bottom, we have unit and component tests written in C++, because it's the main language of HANA, it's the main language of all developers. But if you start writing some kind of integration tests, or very complex end-to-end tests, or so, then C++ doesn't fit very well anymore, and most of the tests are then written in Python. One disadvantage is that if you write more complex tests, more integration tests, they will be a little bit slower and will be more expensive. So unit tests are much faster and are much, much cheaper, typically. So let's take a look at our development process and how we integrate testing and quality assurance in this development process. A developer pushes a change into our Garrett. Garrett is a very famous Git code review system, and the whole HANA source code lives in one big Git repository. After the push from the developer, we trigger some quality assurance processes before the commit even reach any kind of branch. So there will be no commit which will reach inside of a branch without testing, without building. And after the building and test processes are complete, and also other quality assurance things like code analysis, style checkers, or sanitizers in the C++ coding, there will be a review from a very dedicated team which reviews your test results, and at the end they are voting, okay, it's good enough, or please try again and please fix some failures. And after the review, your change will get merged into the repository. So to build something like this, I mean, it's a very straightforward continuous integration landscape. It's also very common to do this. So in 2010, it was like a very common landscape. So developer is pushing to Garrett. Garrett will notify our Jenkins CI server about a new change. Jenkins will look in the configuration. Maybe there's a job configuration for it, and then it will trigger this job, place it basically in a queue, and if there are some nodes without or with available resources, one node will grab the job from the queue and execute them. Very straightforward. Let's take a deeper look into what such a job looks like. Such job is basically divided in 4 parts. So you have to check out the latest source code. You have to build the database from the source code itself. We set up a complete database, and then we run the test. Very straightforward, and until now looks like everyone basically does in continuous integration. And one special thing is already included in the 2010 version. We have a central database, because we are a database department, and we store all our test results in this central database. And the developer can afterwards take a look on this data via web UI, and we can still access on this old data, and I can still review test results from 2010. It's actually not so interesting anymore, but we are still able to do it. So if you read the description of this talk is about scaling and how we scaled our test infrastructure. So the main question is, so why should I talk now about scaling? So, because until now it looks like a very typical continuous integration system. So let me try to prove it, that maybe we have some experience with scaling. So right now our system is working for 600 developers, totally distributed across the globe. This developer is pushing around 700 commits every day into the system, into the repository. We have above 30 million lines of Python testing coding in our repository, and we are performing actually every day testing of 36,000 hours. So this is basically around 4 years. So we are running tests every day of 4 years. We do this on a landscape of small 1,300 Jenkins nodes. And these Jenkins nodes are actually not so small, so we don't talking about RVS small editions. We are talking about bare metal servers in most of the cases. And we are using around 408 terabyte of memory for testing. It's just about testing. So we have much bigger systems with memory, but we are still using 408 terabyte for testing. So let's talk a little bit about how we did the scaling, and I just picked 4 topics for scaling. So one interesting part is test runtime, how we optimize that. Test scheduling is also quite important thing. Artifacts is also a very interesting area because you cannot move so much data around. And then you have to provide a very healthy test environment, especially if you test on bare metal systems. Let's take first about test runtime itself. So this slide shows the runtime of a Jenkins job of around 8 hours. And you can see the job doesn't fit anymore on the slide. So you're pushing and you're waiting more than 8 hours until your test result is available, until you know if everything works well. It's not so great actually from a developer perspective. And we started to optimize it by applying a very common pattern from computer science, divide and conquer, or in our area it's basically divide and test. So the first thing we did was we separated the test job from the build job itself, which means we can now run the build on a different machine, on maybe a machine which is optimized for building our product. And at the end, we run the test on a machine which is optimized for testing. So a very common example is that build machines has typically more CPUs and test machines has more memory. So, but actually this split now increased the time because you have now also this communication time, you have to transfer the artifacts across the network to the different hosts. But this was a prerequisite. Now we can also split the test block into smaller test blocks, which has also the benefit that in case one test block fails, then we can reschedule it and we can still keep the time for review by around 7-8 hours, which is actually good enough right now. So let's talk a little bit more about test failures in our case. Tests can fail, and actually it's the intention of test. So you wrote something new, you don't thought about a maybe unrelated component, and now the test is broken. In case the test is broken, we currently run the strategy to rerun this test, to verify that this is now a real regression. You really broke something, and it's not caused by some sporadic failures, some kind of network latency issues, or some kind of general infrastructure problems, and so on. So after the rerun is complete, and in case the rerun is still, in a failed state, then we know, okay, it's a real regression, and someone has to take a look at the results and take a look at the traces and decide, okay, what is the reason for this? So the main question is, who restarts failed tests? So you can imagine in case a developer pushes something and then goes, for example, home, he actually doesn't want to get in the office at the morning and see, okay, test failed, I have to restart it, have to wait 8 hours or 1 hour until the test result is available. So this is the reason why we started to thinking about a more intelligent test scheduling. And we thought more about test scheduling, and we found out that test scheduling is basically about 2 parts. The first part is about configuration. Which tests should now run? Which tests are now interesting for this change? So, for example, we have different configuration for our multiple hundred Git branches with different components inside, that if you push in your topic branch, which is something like a feature branch, then we will run tests optimized or tests basically for this particular feature. If you push against one of our integration branches, then we will run a huge suite of tests to avoid regressions in other components and so on. But we can also integrate things, and we also added features like layer testing, which means we first do some kind of unit testing. So we run first the unit tests in our infrastructure, and first after this unit tests are successful, we run the really expensive integration test, and then we run the really expensive end-to-end tests. And as we have a large developer base and a large code base, it can happen that someone breaks a test, and in case of you have a broken test, you cannot stop to integrate new changes in your integration branches. It wouldn't work in such scale anymore, and this is the reason why we have also some features and ways to handle such broken tests. So you can, for example, move a test into a quarantine and say, okay, we know this test is currently unstable, there are some bugs inside, and we exclude this test in the execution to save runtime. The other big thing about test scheduling is to observe the whole test run. So in case there's a failed test, he reschedules the thing. Or in case the test is now complete, he can automatically perform a review of the test. And the most important thing is basically after someone pushed something, you actually want to know, okay, now it's complete because the test just runs 8 hours. For this, we started to implement a more intelligent test scheduler, obviously in Python, because we really love Python, which means after a build, the build will trigger our more advanced test scheduling. We call it the waiter, and the waiter will then ask different systems about configuration, about states of certain things. So for example, in case you push something and you reference a bug inside of it, then we will take a look at the state of this bug, and only in case this bug is in a defined state in the process, we will then start the test execution. After the waiter decided which test should run, he will schedule it in Jenkins and will still monitor it, and in case there's a failure or some test block is missing or something, he will reschedule it. At such scale, we have also to talk about queuing in scheduling of tests. So we have certain requirements. So for example, our nightly test should be completed in the morning, or that bug fixes are a little bit more important than new features, so the test should run with a higher priority. And also that we should maybe finish the testing of commits in case they are not fully tested and we have some reruns. Jenkins currently only provides a first in, first out queue, and with first in, first out, it's really hard to implement such requirements. And our solution for this was also to implement it in Python again, because we love Python. So we built a prioritized test queue, which means the waiter is putting now the tasks to run a certain test into this queue, and this queue will sort them around based on the priority, based on the content of test task, and then a processor will fetch queue items from the prioritized queue and will distribute it across Jenkins hosts, Jenkins masters, which is actually also a very required feature to distribute across Jenkins masters, because we just learned that Jenkins doesn't scale well with more than 350 server inside. So let's talk a little bit about artifacts. One thing is that our installer is a little bit bigger than typical software products or than a typical Python package. Our installer is still 15 gigabytes and is living on an NFS share. After the build is complete, they will place the installer on this share, and we will install from this share. And we have also test data in various ranges, something like 4 megabytes, but also above or until 800 gigabytes. And we are doing per week, actually, 9 petabytes of data transfers just to transferring the installer and test data to the real hosts which are running the tests. And to optimize this, we introduced some kind of caching. So we just place a very simple Python script. It's around 800 lines of code before we call the installer, and he will check is the installer already locally available, and in case there's a cache miss, he will fetch the installer from the NFS share, place it locally in the cache, and then we can run the installer right away from it. And we can also do the same thing for test data. So in case a test requesting some specific test data artifact, we intercept this call, and then we are fetching the artifact from the central shares on the local disk, and we can import it. And with this, we actually saved a lot of traffic, and these implementations are very straightforward and very easy. And we saved 66% of traffic, and we are now only transferring, it's still much, but it's better than 9 petabytes, so we are still transferring 3 petabytes of test artifacts every week across our network. The next very important thing, especially in such a test environment, is that you have a very healthy test environment. So you have to make sure that all your external dependencies are available. So as I mentioned, we have this NFS shares with artifacts, with test data, but we are also testing distributed systems. So your local host is not the only host which is currently interesting for your test run. And as we know, external dependencies will always fail. But we have also to make sure that your local system is in a healthy state. As we are performing parallel testing on the same host, we have to make sure that there's no noisy neighbor around on the same host, a noisy test basically running on the host, which, for example, consumes all the available memory. And then it's very logical that your test will fail because there's no memory available anymore. So to solve this, we started and implemented a health check, which runs before and after a certain test run. And it checks all these dependencies, availability of external services, local memory usage, CPU usage, and so on. And also implemented in Python. So what does it look like today? Today we have still Gerrit, but Gerrit doesn't trigger any more Jenkins directly, or there's no Gerrit trigger anymore available. We have now dedicated infrastructure for building the database itself. And after the build is complete, we get some notification, and we will start our waiter, which will then schedule the test tasks, and then some test processors will distribute them across our Jenkins landscape. And the nice part is that if we now take a look what is currently running in our infrastructure, we will see a lot of things are now totally written in Python. So every blue box is now in Python. Also the build infrastructure is heavily implemented in Python. And we still have our central database with all the results and the web UI to review these results. And we are still heavy Python fans. So it's still very great that the learning curve is so easy to get started that non-developers can write tests for us for the database. We are very big fans of the community, so we are heavily relying on open source tools like virtualenv, like pip. We are a heavy user of Sentry, so we are storing a lot of exceptions in Sentry. We are big fans of the development velocity. Performance is nice, but to bring a feature which you had in mind in the morning at the afternoon into production is much better, actually. And that Python is platform independent allowed us also to scale across typical architectures. So currently we are running tests on 3 different CPU architectures and over 10 different operating systems versions. So just give me a very short outlook what we are currently doing and what we are currently trying to achieve. So we are currently thinking how we scale for across 3,000 nodes. We have some POCs running with Apache Mesos for doing a more resource-based scheduling approach. We are playing a lot around with Linux containers, currently Docker, but maybe some other container engines could be also interesting to limit resources to ensure that your test run has enough resources locally available. And we are currently in the step to migrate to Python 3, so a lot of the code base is still on Python 2, but there are some projects already migrated to Python 3. So thank you very much. We are still hiring, so in case you want to play around with a lot of memory, you should definitely talk with me. So I think we have enough memory for everyone. Thank you.
Yeah, thank you, Christoph. Are there questions?
Hello, thank you for the presentation. I'm curious about how do you test the failure scenarios? Like I think Anna has like the distributed structure. Does it test on the Jenkins side, or do you test it with like the Python?
So we're testing it in Python itself. So in case you have a distributed system like HANA, it's possible for the developer to write test cases to say, okay, now I would like to intercept a certain network communication, for example, and then you can test the behavior, how it now works without network between 2 nodes, for example.
Thank you.
Hello, thank you for your talk. One question you mentioned, you run relevant tests first for topic branches. How do you do that? Like, does a developer have to define them, or are you able to determine that automatically?
Currently it's configured. So the developer says, okay, I would like to run this test in my branch. But we're thinking about ways how you map, for example, source code to testing, to test coding, and then we can decide, okay, what should run. And we have also some proof of concepts running to use our coverage data, for example, for such things.
Hello. How do you split up your test suites so that they could run in under 8 hours? Do you do it by hand, or do you have something interesting scheduling methods or something?
We are currently doing mostly by hand. So one of this test block contains multiple Python test scripts, actually, and then we are trying to pick them together to reach a runtime which is acceptable for us. We have some scripts which can generate these collections, but it's not so sophisticated.
More questions? I have a question. Also, performance tests part of the suite?
Yes, we are also doing performance tests with actually the same landscape. So all the performance tests, or many performance tests, are written in Python also. And we are doing also a lot of reporting and evaluation of the results of performance testing with Python.
Cool. More questions? That's not the case, so let's thank Christoph again. And as usual, please remember to rate this talk in the app so he has some feedback and also the organizers get some feedback.
So welcome to the PyCharm room. The next session will be by Anand, who will be talking to us about how to write beautiful Python code. So,
thank you.
Anand.
Good afternoon. So I'm going to talk about something that's dear to my heart, writing beautiful code. So before I start, let me introduce myself. So my name is Anand. I teach Python professionally. I conduct advanced programming courses at People Academy. I'm also a co-founder of a startup called RoroData. We're building a data science platform there. So I use Python heavily at my work and also teach whatever I learn to students. So let me start with a quote from Christopher Alexander, who coined the term the pattern language. So it's very hard to say what is beautiful. Have you ever looked at a code and actually felt, wow, this really looks awesome? Like, have you ever felt? Raise your hands. Yeah. Yeah. So it's really hard to say what a code is beautiful, what makes a code beautiful. Okay. So it's kind of, some people say it's, Christopher Alexander says it's the quality without a name. So you look at it, you kind of feel it, but it's very hard to say. So he talks in the context of architecture, but applies to many other art forms as well, if you consider programming is also an art. So let me quote this from, it's called the Wizard book, Structure and Interpretation of Computer Programs. It says programs must be written for people to read and only instantly for machines to execute. It's a profound statement because usually we think programs are written to just get some job done. Okay, so we write for computer to execute something. But if you look at it deeply, programs must be written for people. The reason is, if you look at the life cycle of any typical computer program, write once, first time for the computer, for the remaining duration of the lifetime of the program. Sometime, I mean, someone else look at the program after some time, he has to understand that code. Or a lot of times what happens is we write a code and after a week or two, we just can't make sense of that program. I'm sure like all of us went through that phase. Okay, so it's very important to write programs to keep in mind of the people who are going to read the code at a later point. So we should always try to improve the readability of the programs. So let me start with the very simple low-hanging fruit that everyone knows that you have to do it, but not many people do this. Okay, choosing meaningful variable names. It's so important that even people with a lot of experience fail to pay attention to this. I teach Python professionally. I do Python, advanced Python courses to working professionals. So I really find it frustrating when people with like 3-4 years of programming experience and they can't even pick right variable name. It's not that they can't pick, but it's just that we don't just pay the attention to those details. I'm going to show you with a couple of examples how important it is to pick a right variable name. So let me quote Phil Cullen on that two hard things in computer science are cache invalidation and naming things. Believe me, naming things is not easy. It's hard. What's the longest time you have spent banging your head to figure out what name to give to a class or a file name or a variable? I remember spending literally 2 full days to figure out what should I name this thing, what I'm trying to implement. Okay, so naming things takes time, and you should give that time. Okay, it's very, very important to give that. So the first tip is avoid generic names. They really don't make sense. If you want to, so what we do is we want to have temporary variable, temp to manage your data. It's kind of, there's 2 generic names. You really can't understand what they mean. You have to use a little more specific names, for example. Yeah, so you should use a little more specific names to the context what that means. The other thing is, hope you can see the colors. Yeah. So the red is to indicate not so nice code, and the green is the one which is what I'm suggesting. So avoid using abbreviations. People say UCF, uppercase formatter, but people can't understand what UCF is. It's okay if it's saying HTTP or SMTP because that's a well understood acronym, so that's fine. But using something like BA for a bank account doesn't make sense. Okay, it's very hard to understand. You can probably say formatter or an account or something. So that's I think a good thumb rule. Don't use abbreviations unless that's a very common thing that everyone knows. This is other common mistakes that I keep finding in people is they use a data type as a name of the variable. They say it's a list. They say it's a string. Okay, but list of what? String holding what, right? So it's better to say actually what it says. It says sum of numbers, count words. It takes a string, but actually a sentence. It's not a paragraph. It's not a file name. So it's better to say specifically what it actually means, not just saying the type of it. So that makes it a lot more readable. The other thumb rule about nouns and verbs is to use nouns for variables and classes, saying concepts, and use verbs for functions, so saying actions. So these are the tasks that you want to do. So size, price, task, scheduler, etc. They go well for variables and classes. And use actions. Get file name. Instead of just saying a function as file name, say get file name, so that it kind of indicates you're doing an action, or make account, or deposit. So these are the kind of examples where using verbs makes sense for functions. And okay, these are not it's very simple rules, not something that I invented. These are the age-old wisdom that's been talked about from so many people. If you find out practice of programming, or there's so many other books people have written, but I'm just trying to take that wisdom and put in the context of Python. So if you look at, if you have a list of values, it's good to use a plural for that. So say largest line of lines, or OS listed directory, and you get files there. But look at the other example. So file equal to OS.listed directory. It's not a file, it's a list of files. So it's better to use a plural to say that it's actually a list of values. And these are examples actually, real world examples have found from people when I'm doing teaching. Okay. So people say for lines in open file name.read lines. Read lines gives you a list of lines. Each element is a single line, not lines. So and saying int of lines doesn't make sense at all, right? So it's better to use plural for a list. And when you're using loop indices, reserve I and j for loop indexes only, not for the values. Okay. For example, for I in range 10 is fine. I is an index you're going over its value 0 to 10. But if you're going over a list of values, using I doesn't make sense, because I usually use for an index. And if you're using I for numbers, that feels like it's a single integer, but n could be a number, or it could be a string or anything, right? So use something which is more conveys what it actually holds. For n in numbers, probably makes a lot more sense. You might be thinking like, why am I talking about silly things, right? These are things what everyone knows, but it's really, really hard to get this in practice. Okay, let me show you an example. This is a small file and function I've written. Okay. Can you just try and understand what this is doing? Can someone, let's take a minute and then see what this does. Can someone explain to me what this function does? Yeah?
Extract a column from a two-dimensional list.
Wow, awesome. Yeah, that's what it does. Okay, but let's look at this. Okay, so if you look at the same function I've written like that, okay, all I've done is I've changed the names. I've not changed any structure of the program. So it's just a file and program, and it's really hard to understand what is doing X and Y, and they're adding things to Z. Okay, so by changing the names, it made so much of a difference. Okay, now by looking at it immediately, you know that it's a data set, it's an index, and you're taking a row, and then from the row you're taking, yes. I know, but the thing is, I'm talking about, I agree. So I picked this example because to show how much difference names makes. I agree, you can use list comprehension, but just trying to show how much names makes sense, okay? So if a file and code can make so much of a difference in picking the right variable names, imagine what would happen if you're working with a 500-line program or 10,000-line program, right? So it's really, really important to pick the right names. So the other thing is when you're using similar names for completely different data types, it's kind of very confusing. So when you're writing code, you should also keep in mind what people think unconsciously. Okay, so when you see names which are sounding similar, we unconsciously expect that they actually hold similar type of values. Say A1 and A2, you think they must be the same kind of values. But if you put a list in one other integer, that's very, very confusing. It's very hard to make sense of that. So probably say values are n instead of saying A1 and A2. And that's one of the issues that we had in the previous example as well. We say x and y, kind of feels like x and y must be the same types. Maybe both are lists or both are integers or something, but they're not. Okay. Now let's look at comments. We all say writing comments is good, but is it really? I mean, there's really no need to say the obvious. Okay, increment x by 2, but it's okay. I mean, Python programmers will look at the Python code and figure out we're incrementing x by 2. But that's the obvious thing. There's no need to write a comment, but you can actually explain why you're doing it. Compensate for border on both sides. So you're adding 1 pixel on both sides, so you're adding 2. So that makes more sense. You're conveying why you're doing that. So don't say the obvious, say why you're doing that. And a lot of times it makes a lot of sense when you're commenting, add a comment to explain why you made that choice. So the following is an optimization, saves a lot of memcache calls. So I'm saying that this is the reason why the following code is being done this way. And also, it's good to document special cases. For example, you figured out there is an Unicode error happening, and you don't know what's happening, and this magically fixes that issue. Okay, so put a timestamp and say, this is a special case, and this is how I'm fixing it. So in future, people will be careful when you're touching that part of code. And it's actually good if you can actually make comments redundant. Okay, you can write code such a way that you don't really need to write comments. For example, if you look at the first case, the find length of the longest line. So it's a list comprehension and finding the max of that. Okay. Instead of that, if you say n equal len of longest lines, you don't really have to comment that. It's kind of very clear in the program itself. So you can write self-documented code. So the code is simple enough for people to understand by the code itself. You don't have to write the documentation. So that's something really awesome if you could do that. Yeah, the other thing is, if you have longer functions, what we typically do is you have stage 1, stage 2, add a block comment, say that this is what, so process documents and upload them to search engine, and there's a part of code. But it makes more sense to split that into smaller functions, and then say docs equal to process documents, and then search and submit to search engine. So you don't really need comments to explain that part of code. Now that we have looked at the simple things or more accessible things like variable names and comments, let's look at program organization. So how do you structure your program? So divide and conquer. So split your program into smaller independent modules and functions. That way it's a lot easier for people to make sense of that. Let me quote Miller's law. What it says is, number of objects the average human can hold in working memory is 7 plus or minus 2. It has profound implications on how we should write our code. The reason is 7 plus or minus 2 is the number of things that you can hold in your head. That probably means when you're writing a function, you should not have more lines than that. Or you have a class, then the number of methods that in your public API should not be more than that. So when someone looks at your class and then starts working on it, starts using it, if it has 7 plus or 2 minus functions, then you're able to kind of keep all of it in his working memory and then able to work with it. But if it has a lot of them, it's pretty difficult. So that's a kind of ballpark figure to keep in mind when you're writing classes or functions. So I think that's a good number to keep the size of a function as well. And the other common thing people always don't pay attention as is duplication. So duplication is bad. So for example, it's a function, it takes an input data and tries to convert that to an integer and then sums them up and give the value back. Okay. So since let's say data is coming from users, we want to do some validation and converting to integer before we actually do the summing up. So there's an try and except, but we're doing it twice. if you see, actually, I've deliberately added in. So just people write one thing and then copy paste and then modify things, and you see, I kind of deliberately left X here because that's kind of errors that we usually get into. Okay, so instead of duplicating, it's a lot better if you can actually generalize that. Say you get int, take input data, and then X and Y, and you return X and Y. So if you look at the add function here, it's very easy to understand now than what we had before. Now, we should also avoid too many nested levels when you have a function. It may have, so we may end up like writing code like this. It's updating a blog post. So there are many cases where you want to update a blog post. You want to update a title or a tag. So there's a big function that kind of going over the steps. But if you see there are too many levels of, too many nested levels here. So that's kind of hard to understand. So what can be done is you can take each part of that and then make that into a separate function. That really makes it a lot more readable. Okay. So if you look at this function is just delegating it to other sub-functions. So if you look at this function, it's easy to understand. And if you want the further details, you can look at each of these other functions. The other useful thing is to make sure you handle errors separately. For example, this function is trying to get user from given the email address. So you first check it's a valid user or not. If it's a valid user, just make sure the account is not blocked. And then you query the database and give the user back. But if you see, the core of the function, the main function of this, this function is hidden in 2 levels deep. Okay, so the query, so the database querying is the core of the function, but that's hidden deep inside so many if conditions. Okay, so wouldn't it be better that to be the most prominent part of the function? So what you can do is you can keep the errors handling separate, for example, like this. So you do the error validation first, and then in the top level you have the core of the functionality. So you get a query and then query the database, get the results. And if you're really trying to understand this function, you could just skip the error validation and then directly jump to the main part of the function, which is not so straightforward if you're doing it like this. Now, the other very important thing is we should try to suppress implementation detail as much as possible. The reason is when someone is trying to understand program, the intent, what the program is doing and how the program are doing are 2 different things. So when someone comes to your program, he is more interested to understand what the program is doing, right? So we should suppress implementation details as much as possible so that you can understand the intent of the program pretty quickly. And then if required, you can go and then see what each of those functions are doing. For example, this program takes one command argument, which is a file name, and then reads all the words in the file, computes the frequency of the words, and prints the frequency. This is what the program is doing. So it has 4 lines, and this is all the program is doing. So the intent, what the program is doing, is very clear by looking at this program. Okay, but if you write a longer function and then put in how the words are read and how word frequency is computed right here in the same function, it becomes too difficult to understand why someone is doing it. Now, you know, they're reading word frequency, computing word frequency. I can go to word frequency function and figure out how it's actually being done. The implementation and the intent can actually be separated. The how and what, it's good to separate those 2 things together. So now, that's, I think, the things that I want to mention about the writing beautiful code, and this is a quick summary of what I've covered so far. So choose meaningful variable names. I can't stress enough how important it is. Sometimes it takes a lot of time, but it's worth spending the time because the amount of time we spend later trying to figure out why the program is written like that or trying to figure out how this is actually working is a lot more if you don't spend enough time early to pick right variable names. And use comments when required, but don't put comments just because you have to. Split the program into small independent modules and functions. Avoid duplication at all costs. Suppress implementation details and always optimize for readability. Let me stop with a quote from Tower of Programming. A program should be light and agile. Its subroutines connected like a string of pearls. So talking about the elegance of the program, the spirit and intent of the program should be retained throughout. Should have the clarity that you should have in the program. There should neither be too little nor too much, neither needed loops nor useless variables, neither lack of structure nor overwhelming rigidity. And also you need to have the right balance in your program to make it beautiful. Happy coding, and I'm open for questions. The slides of the talk are on my Twitter feed if you can find out if you want to follow that.
Okay,
I'm open for questions if you have any.
Please wait for the mic. Yep.
Hi, so when you talked about the number of objects that the human brain can track, what's your opinion on the sort of recommended maximum minimum length of a code block?
Sorry?
Like the sort of recommended length of a code block, so there's a school of thought that says if a code block is larger than n lines, it becomes hard to read, where n is said to be any number between 40
Yeah,
and
so I think thumb rule is it shouldn't be more than half a page of sheet, I think is what people say, but I would say, I mean, my usual recommendation is not more than 10 lines is what maximum I would say for a function. So I would say like the 7 plus or minus 2 rule, it works for even number of lines in a function.
What are your thoughts on code formatters like YAPF?
Sorry, could you please repeat? I couldn't.
What are your thoughts on code formatting tools like YAPF?
I think it's I think let me repeat. So you're talking about the Go format tool, right? Yeah, I think it's a really good tool. I think it's called the bike share discussions, right? Should they use one space or two space or put a space before or after? I think we just get used to whatever it is. And I think Go has really done very good thing about having, you don't have options, you have just follow just one formatting thing. But I don't think we have that luxury in Python. Though there's Pepper 8, it's up to the people to decide whether to follow or not. I think I would really love to have something like that for Python.
So just a quick question on your thoughts on something more specific about intelligible variable names. I agree with most of what you said. I think it's great. I just wondered about this habit of deleting all the vowels in variable names, like trying to, like picking a name and then abbreviating it by deleting all the vowels. Like, I hate this. What do you think about it? This practice.
Sorry, I didn't get. Could you please repeat the question?
Sorry, yeah, so this kind of habit of deleting all the vowels in variable names once you've chosen a name, that to try and make it shorter, like I guess there's a trade-off between variable length and intelligibility.
Yes, so I think it's an important point. So I would say the variable, the length of the variable should be can be proportional to the scope of it is. Okay, so for example, if it's a local variable, if you have a function which is 5-6 lines, it's probably okay to have a single letter variable. But whereas if you have a global variable, which the scope is much larger, it's better to be verbose and have the full name. So if it's just a small function or inside a for loop, I would say for W in words, W kind of indicates it's a part of it's an element of words, so that's a single word. So that's probably okay to have a single letter. But I don't really like to take out vowels or kind of make it short just to, I think readability is more important than the length of a variable. That's what I would say.
Any more questions?
Thank you, Anand. In your opinion, what is a good time to clean up your code when programming?
I would say it's a habit that you have to build over time. Okay, so once we start keeping these things in mind when you're writing code or looking at someone's code, we kind of feel that, hey, it's kind of violating that principle. Okay, so we should start getting that sense of identifying that bad smells, so that when you're writing your code, you don't actually write that kind of things. I mean, probably when you're beginning, for a beginner, it probably takes a while to get that habit. So you'll write it and then clean up. But once you get through that, go through that habit, you'll probably start getting that sense. It kind of becomes your habit, I believe.
Any more questions? Nope. Okay, so thanks a lot, Anand.
Thanks.
We will have a 10 minutes Hello everybody. This is the last talk of the evening before the lightning talks. Christian will be talking about or giving us some best practices for Python. An applause for him.
Welcome everybody. When I was 15 years old, I was writing a computer game, a little bit like this one. I wrote this on a C64 computer in the assembly language. Is anyone here in the room who has tried doing that, actually? One or two? A few people, great, congratulations. Well, I was writing, this was my first bigger program I wrote in assembler. And the way it was like, I wrote a couple of lines, tried to run the program. Usually the computer would crash. And so I switched it off, waited a few seconds, switched it on again, loaded the computer, the compiler, loaded my source code, and the entire process repeated. Needless to say that you won't program very fast doing this because my average debug run cycle was about 10 minutes. And this led to a lot of frustration. At the moment, my game is 24 years behind schedule. Only later I learned that on the C64 we had devices like this one, a small cartridge that you could plug in the back of the computer. It had a button on it, you push it, and you jump right into the compiler, can edit your code, and continue where you stopped a few seconds ago. But I was totally unaware of that. And basically, the aim of my talk is to prevent us from pitfalls like this one in Python projects. Now, I'm not going to talk about anything fancy or totally new here, because what I want to address is a common problem that I have observed happening when people are new to Python or are a little bit more advanced in Python. After you mastered the Python basics, you pretty soon figure out that there are plenty of libraries. For instance, if I want to do data analysis, then I need to find a library for data analysis, like pandas. If I want to do, I don't know, signal processing or Fourier transformation, then I Google a library for that and find SciPy, for instance. Or if I want to do web development, then I will find Django, and so on. These things on the left side, they are easy to find. Even if I don't know them, I may have a hunch that something like this must exist. But the ones on the right side, if I have no idea that something like interactive debuggers exist, then I won't be looking for one. The same goes for automated testing, and the same goes for all the tools in the Python ecosystem that help support and maintain our code. And I want to shed a light on these dark spots. So if you walk out of this room and see, hey, I haven't learned anything new, then consider this an additional safety check. Pretty much like if people start an aeroplane, pilots, they have a checklist that they go, okay, do we have clearance from the tower? Are there any other planes on the runway? Do we have enough fuel for an emergency landing? And so on and so on. And I think it's good to have something like that in a programming project too, and this is why I call it best practices. And my talk is split into 3 parts. I would first like to talk about debugging, then show an example of about testing, and then about maintenance. Debugging. When you talk about debugging in Python, the first thing that comes into your mind might be print. Now, print is something that I consider a bit problematic. even though I do it a lot. Because it's like shooting holes into a building to see whether there's a fire inside. Every time you add a print statement to a piece of code, there is a risk that when deleting the print statement, you delete one line too much without noticing. And this is why it's worth keeping in mind that there are other debugging techniques. For instance, the interactive debugger. For instance, logging. With the standard logging module, this is really an excellent way to produce diagnostic information. If your program is bigger than a couple of screen pages, then logging becomes superior to print after a while. You need to know your introspection functions like dir and type is instance and a couple of their cousins. And I put code review here as a best practice that helps with debugging a lot. We had a tutorial on debugging yesterday. If you were attending some other part of the conference, the exercises are there on GitHub. You can try them out by yourself. But what about the really tough bugs? If something does not work and does not work, you stare at the code and go on staring at your code without any progress. I'm sure that this has happened to most of you in the room. At least it happens to me still after 28 years of programming. And I have figured out something very nasty over the years. Not that I'm lacking some additional best practice for debugging here, because 9 out of 10 times the problem is inside my head rather than in the computer. And fortunately, there are ways to fix that. So I would like to add to those best practices of debugging 4 very elementary things: sleep, talk, read, and write. Most of the time, if I spend more than 15 minutes on a bug and I don't find the solution, then I'm probably tired. Often it helps to talk to another person explaining what you do, to realize what the problem really is. Maybe I'm looking in the wrong spot, and explaining helps usually. Sometimes my knowledge is limited, and reading the manual of the library, this time for real, helps. And if all of these fail, writing down what the program is, formulating a couple of hypotheses, or at least ideas what the problem might be, could lead to progress. Most of the time I'm lazy and take a break, and this has solved lots of bugs in the past for me. Testing. The check icon here is actually a bit of a provocation, because this suggests something that automated testing does not do. Testing actually does not prove correctness of your program. I know that many Python developers, they love automated testing. I like to write automated tests and run them. It gives a feeling of achievement. Yeah? But there's a pitfall, and the pitfall is that one in the bottom right corner. If there's always a possibility, if my tests pass, it could be that both the code and the tests are incorrect, even if I try hard to keep my tests as simple as possible. So tests by themselves do not prove correctness of the code, but they have a potential to prove the presence of bugs. So if I see a failing test, I know that somewhere something is wrong. Now, how can we write good tests actually? Let's imagine we are writing the game, this time in Python, not in assembly. This grew too tiresome. We have a figure that is pushing these blue boxes around. It can only push one box at a time, cannot push any boxes through the wall, and so on, until you reach the exit here in the bottom right. Now, how could a test for this situation look like? The first thing that you can think of is a fixture in PyTest. I learned today when talking to the PyTest core developers that it's a good idea to place fixtures in a file conf_test.py, and because they get automatically imported into all your test files. Now, fixtures are actually pretty straightforward. You decorate a function with the PyTest fixture decorator, and the name of the function will be available as a variable in all your test functions if you put it there as a parameter. So in that case, we could have a level parameter available in our test that then contains a parsed version of our example game situation. Actually, I did something additional here. I parameterized the test. So there are two versions of the playing field supplied to the test, one with empty spaces and one with dots on the playing field. So I can have two fixtures or more in one by parameterization. And then we can use this in a test function. I like to group my test functions into classes. With PyTest, this is fortunately a lot easier than it used to be with unit test. I still have less boilerplate code. So I can write a normal test function with just an assertion that is self-sufficient, or I can use the level parameter here. Note that I'm not importing level anywhere. This gets automatically filled in by PyTest. Yeah? And this test function will generate two tests for me, one for each of the variants in the fixture. What else can we do? The third most important thing that I would like to emphasize about automated testing is test parameterization. So we can have one test function write try multiple examples, like here. We say by this parameterized decorator, we would like to try out all the examples in the list, like having a move that goes first up and then left, and afterwards the playing figure should end up on square 2x and 2y. It's even possible to build failing tests with this, or tests that we expect to be failing. So we have still write only one test function, but with this one we would generate 8 tests in total. So it saves a lot of code. The code becomes actually very readable, and if we end up in a situation where our test code is ridiculously easy to read, much easier than the code we are testing, then we are on the right track. So if we execute this code by writing PyTest, this is another thing I learned this morning, that the dot inside PyTest has been deprecated. We can use PyTest without the dot in the middle. So we see that all the tests execute. This test actually uses a window, and we see 34 passed tests in the entire test set. Not only the ones that I showed on the slide, there's a few more running in the back, plus 2 that are expected to fail because I marked them with the xfail decorator. Now, how much testing code should you write? In my opinion, this depends quite a lot on the size of your project. If your project is small and prints an obvious result anyway, then maybe a manual test is enough unless you want this to be continuously integrated. Sometimes I still write test code in the main block of a small Python module. I can make automated PyTest functions out of this quite easily later if the project grows, add some fixtures as the thing grows further, and if the program keeps growing and growing, then at some point it might be helpful to switch on testing tools like Jenkins, Travis for continuous integration, or Tox for testing multiple Python versions. When I speak about size of the project, this can mean different things. It could be absolute volume in lines of code, but it could also be the expected lifetime of the project. So if I expect code to be maintained for 2 weeks, then I would not worry too much about testing if I'm writing a throwaway program. If the program has a high dependability, so if it needs to be extra safe, then doing more tests and reviews and things like that is also a good idea. In the final part of my talk, I would like to elaborate on maintenance. Python has a fairly sophisticated ecosystem of maintenance tools. Yeah? And they serve the single purpose of keeping your code in a good shape, like PEP 8 being a layer of paint on your program, like many of you probably have heard in the talk of Anand a while ago. Making beautiful code is a virtue, and Python has nice tool support to help you with that. Instead of picking a few must-have tools, I tried to throw in some that keep reoccurring, with Git being in the middle, being not a coincidence. So if there's anyone not using Git or version control yet in the moment, this conference is a good starting point to learn that, because you won't be getting anywhere without version control. But others, there are many other tools as well. Some of them are interchangeable, like PyScaffold, recently in my personal ranking surpassed by Cookie Cutter. There is Sphinx for documentation, virtualenv and pyenv for managing your Python installations and libraries, Pyland and PyFlakes for watching your coding style, and so on and so on. Now, what can you do to keep an overview of all of these tools? Now, I would like to just mention two possibilities here. One of them is Magdalena Rother is going to give a talk this Friday where she's going to give an overview of all the different configuration files that you can find in a well-maintained Python project. So this is on Friday afternoon. If this is still too far away in the future, I recommend you to take a look at Koala. Koala, some of you may have noticed that there's a flyer in the conference bag. I visited the Koala booth yesterday, and the developers actually gave me a quick introduction, and I was able to run Koala within 5 minutes or 10 minutes. So Koala is a framework that basically hosts many linting tools. That means tools like PyLint or MyPy or other tools that analyze the quality of your code, not just for Python. And I thought, how awesome is that? I can check not only my Python files, I can also check my HTML templates and JavaScript code and whatever has been accumulating in my project, and get everything from one tool that tells me how good it is. So how does that work? Koala brings its own configuration files that mainly contain a list of the tools that you want to switch on for a given type of file. For some reason, Koala calls these different linters bears. So you have a list of bears in this configuration file, which is, in my opinion, it's kind of cute, and I need to say thanks to the developers for doing that. I really appreciate it. And you can put in some additional parameters. What you can do when you have this Koala file set up is that you simply write Koala --ci, and Koala starts scanning your entire code base recursively, analyzes all the Python file, and comes up with a huge list of comments and suggestions for potential improvements. This ranges from sorting imports to style checks or even using a static type checker on Python. So please feel encouraged to try Koala out. I'm not as brave to call this a best practice yet because it's kind of a new tool, but I hope to make that statement next year. Now, this is an overview of testing, debugging, and maintenance practices that I wanted to give here. And there's one more thing that I would like to do. I got into this topic and liked it so much that I wrote a book about it. And I got 3 copies with me that I'm happy to give away. So after the Q&A session, I'm holding a bag open here. So if you put a piece of paper with your name inside, I will draw 3 lucky winners at the end of the session. And you can read more about best practices there. And some of the content, like the debugging tutorial, you will find on my GitHub profile. That's it for my talk. Thank you very much for your attention.
Okay, so we have some time for questions. Any questions? Okay.
Hi. One thing I noticed that you didn't really mention was talking about virtual env and kind of the mismatch of packages with repositories and pip and compiling from source.
So could you repeat the question, please?
So it seems a bit missing about virtual env. Like, surely that's a good practice to use virtual env so you have the correct version of the packages.
So what's the best practice for getting the versions of packages right?
Well, so using a requirements
yes, that's
dependencies file.
Do we have requirements? We have requirements text here on the top of the cloud. So yes, this is the #1 way to go for getting the right versions, because pip can deal with it. Conda should be able to deal with it, and saves you some trouble.
Any more questions? Sure.
So one thing why I was going to say about the requirements thing is so I work with software where the version number is not fine-grained enough. So we actually use Git commits for the actual checkout. But it relates to if in your requirements file, if you don't pin exact versions, if in the future they get updated and functions get deprecated, it ties into your maintenance issue, is that future users won't be able to use your software. So it's just a key point there, if you've not really kind of pointed that out before in talks or in your book. It's an interesting one.
Yeah, this is one of the tougher problems. So I'd be a bit careful with leaving a certain version number in your dependency like forever. I wouldn't do that. Rather check it from time to time, or check a few different ones if a newer one comes out. Because I would not feel comfortable with leaving the version number empty all the time, especially not if you are planning to automatically deploy the code. If you are running the program manually, then okay, I'd feel comfortable with it, but not if you have any automated pipeline running in the back of it.
Is your book also available as an ebook?
Yes, but unfortunately you have to pay for it. Yeah. But it is, yes.
Fair enough. Okay, no more questions then. So that's it.
So,
Applause.